Okay, so good morning, everyone. My name is Wingham Green. I'm from the Atos Bull Company, and I'm glad to welcome all of you to these sessions dedicated to the presentations of the H2020 Evolve project. For this session, so as you can see in the agenda, we will have 5 talks to present successively an introduction to the project, the hardware and software aspects of the Evolve platform, and then the application of this platform to the different use cases of the project, together with the proof of concept, which are part of the ecosystem built around the Evolve platform. So as we have a very tight schedule, I suggest that we defer all the questions to the end of the sessions. And now, without any further delay, may I invite Jean-Thomas Acquaviva from DDN Storage. He's the leader of R&D teams in DDN Storage, and Jean-Thomas is also the project coordinator of the Evolve project. Jean-Thomas to present us now an overview of the project.
Thanks a lot, man. Thanks a lot for the introduction. So let's share the screen. Okay, so Evolve project, a 3-year project. So let's see a bit what do we have in terms of consortium and I will say project structure. So it's an ICT 11 project. So this is an initiative which has been funded by Europe 3 years ago. 4 projects were elected. We are one of them. Evolve is pretty large, 19 partners, a total budget of 14 million euros. And the project will be over in 1 month. So it's time for us basically to share the lesson and maybe also to communicate about the results that we get during this long journey. And an important aspect is this is an innovation action. So the purpose is not only to do research and push the boundaries of science, but also to bring some concrete things to the market. On the right, you can see the consortium, and you will see that there is several companies, large and small, some startups and large group, and also some academic institutions. So the consortium is kind of balanced in order to have the right energy in terms of innovation, science, and synergies. So heterogeneous platform to perform convergence between big data, HPC, and cloud. So that's very nice. So here on this slide, you have the 2 aspects of it. You have the conceptual view on the left, and on the right, this is the real thing. So the system that we have built during the project. So obviously for the project of this size, we need to have some real things where you can run application. So this system is hosted at Bull facility close to Paris, and we are running application on a daily basis. There is a team of sysadmin to help the end user. So it's a real functional HPC system. So on the left part, we can see the architecture, at least a sketch of it. So heterogeneity is mostly at the compute side. So this is on the left where you have these yellow boxes. So yellow box means CPU or processing element. On the top, you have CPU plus GPU. So the green array is the GPU. So it's very classic heterogeneous system. So it's an accelerator. On the bottom, it's a bit more original since the acceleration is not a GPU, but a FPGA. So we have some nice example in the project where FPGA can bring a lot of acceleration, specifically for image processing and signal processing. And on the extreme left, you will see that some of the CPUs, they have also this little graphic like a database. So this is basically system which has been extended, augmented with a local storage. So we open the compute node and we insert a fast NVMe directly on the PCI bus. So it means that to store data, read or write, the CPU does not need to go to the network, but can act locally and completely individually. So this is a local storage. So it's also a way to accelerate and to provide heterogeneity. The only things which is homogeneous in this system is a network. So it's a full fat tree InfiniBand system. And in respect of the storage, there is, so as I mentioned, the local storage for a subset of nodes, but there is also two different tiers. One tier is a burst buffer, so it's a full flash system. We have 8 servers, all full of 24 flash system. So they provide fast results, specifically good for low I/O or small I/O and things like that. But for large capacities, then we move to the second tier, which is based on hard drive, and it's more for capacity. So we have heterogeneity on both axes, compute and data. So obviously, if we have heterogeneities from the hardware part, we have also heterogeneity on the software side, and this is somehow one of the key aspects of this project. So this slide is coming from the BDEC. So thanks BDEC for allowing me to present this slide. On here, what we do see is that this is a software stack from HPC and big data. And even if they share the same ground, so it's a Linux system, actually, these two software stacks have been built in a completely orthogonal way. So for HPC, there is Linux, resource management, numerical libraries on MPI on the application. On the big data world, there is more abstraction layer, mostly because they are dealing with commodity hardware. So for instance, on the top of the operating system, you will start with a virtualization layer, such as containers, and then another virtualization layer. So HDFS basically virtualize the file system. And then we have middleware, and then at the very top, we have the application. So if we want to run HPC application on our system and similarly big data, then we need to be able to we do not want to rewrite everything from scratch, right? So we want to connect the boxes. So we spend a lot of time to build connectors and bridges across these boxes. And one example that we have is that you can run your application on Spark, but Spark will run almost natively on the burst buffer, so with a very high performance. And it's transparent for the end user. It's not aware that he's using burst buffer. It's just a Spark application. So in terms of use cases, we have two big corpus of use cases, so a total of 8 applications. 3 of them are about satellite images, so it's linked to the Copernicus project. And we have Sibeltech, which are analyzing satellite images in order to optimize agriculture production, so they can detect if the crop is growing correctly or not. We have Thales Alenia Space, so they are looking at the same area with different pictures across time, and they can detect changes on the ground thanks to their AI pipeline. Space Hellas is also using satellite images, but it's fusion with other information. So there is correlation between the images and the signal sent by the vessel and by the sea. So they need to send their position to the port or to the authority. So we can check here if the position of the vessel is matching with the declaration of the vessel. So it's a very important thing in order to predict the trajectory and also to enforce basically border control in Europe. The second set of application is related to mobility. So mobility is mostly personal mobility, so cars. So here we have 4 different applications: predictive maintenance for the engine. We have also the next step is basically maintenance for the engine. So if we do not predict correctly, we have to fix it. And depending on the car model and the nature of the problem, then an AI system from Kula, so it's a cool startup from Sarajevo, they can help and ease the maintenance. BMW, they are producing the core algorithm for ride-hailing algorithm. Virtual Vehicle is working on an autonomous driving application. On the other side of the mobility part in Evolve is maybe a bit more, how to say this, eco-friendly. So it's about mass transportation. So we have a public operator from a fleet of buses in the northern part of Italy. And they are working jointly with IT specialists. And the idea is to use the Evolve platform in order to improve the service and to react to hazard. And when you have a large fleet of buses, this is not a trivial task. So additionally to this application, we have another layer, another way to assess the quality of the platform quality, not only in terms of hardware and software, but do we deliver the easiness of utilization? This is a POC. So the issue that we had with the pilot app is that we embed this application at the very beginning of the project. So basically, we are growing together. So hardware, software, middleware, and the application, and there is a kind of co-design. So we get along and we know each other better, and then we improve the things together. That's very nice, but then sometimes the market is a bit more harsh. And this is why we have this notion of proof of concept. Arrive at midterm of the project when the platform is stabilized enough. Then we go and reach out for external user and we propose them to basically to test and try the platform with their own application. So for us, it's a much, I will say, a better reality check. So then we can assess, do we deliver what we are supposed to deliver? Is it not too complicated for external partner and things like that? So the application heterogeneity, so before, so for some of these applications that we start with at the original, it was like just a big piece of monolithic logic. And now at the end of the project, and this is the way that we have basically enforced convergence and heterogeneity, everything is split in workflow. So this is a modern way of doing computation nowadays. So you have different components which are interlinked all together with microservices. And because this component has very specific process, they are going to put the pressure on a different part of the system. So for instance, in my pipeline, if I'm doing simulation, numerical simulation to assess that the growth of the crop is correct based on my model, then I need a lot of floating point numbers. So it's going to be CPU intensive. And then once the result has been produced by the simulator, I want to have some rendering and visualization part of the result. And this workflow stage is going to use massively the GPU. So this way we have a more complex resource management for sure, but then we have a much better efficiency on time to result. So now that we're almost at the end of the project, what is the bottom line? So basically it works, right? So when you inject accelerator into a platform, well, it accelerates, and we have some very nice speed up, so up to 100. But the important point here is that it's not only about you throw more hardware and then you get faster time to result, is that you improve the whole cycle. And in the cycle, there is the end user, there is a developer, and there is the DevOps. So it's also about boosting the productivity. And a large part of Evolve has been to conceal basically the complexity of the system and to provide the right balance between abstraction and accuracy in order to help the end user with few lines of code to express his workflow, but just with enough information so the resource manager can dispatch the stage on the right part of the system. So it's an innovation action. So it's not only about building a very nice HPC grade converged system, but it's also about putting some innovation to the market. So in Evolve, we have produced 12 different innovations. So they do not have all the same level of maturity, but some of them are on the market actually. So I'm going to detail 4 cases, so not the 12, be quiet. So one very nice innovation that we had, DataShim. So it's coming from IBM and it's open source. So it's already quite a result. And this open source project has been selected and hosted by the Linux Foundation. So it's kind of recognition about the quality of the work. And here the idea is to abstract the location of the dataset for a container. So using DataShim, if I move my container, the dataset is going to move to the right node transparently. We have also use this DataShim innovation jointly with MemoPort. It's coming from a Norwegian startup, MemoScale, the partner of the project. And here the idea, same core idea to try to hide the complexity, is that there is a transparent compression between the S3. So you think about like AWS, for instance, S3 server and the S3 client. And if both are running MemPort, then all the data are going to be compressed, and with a very good compression ratio, because the algorithm has been tuned for satellite images. So we can compress up to 60%. So if you consider that downloading data you have to pay on Amazon, then you pay less, then you use less bandwidth, and you have a better time to get your data. So it's a very nice innovation as well. Earth Observer is coming from Thales Alenia Space. So this is a ground detection, excuse me, the change detection.
Jean-Thomas, 1 minute.
Pipeline. Okay, good. And then we have also a visualization algorithm that is used in a very large US government website. So we are very proud of it. So it's not only about innovation, we have also a good throughput in terms of scientific paper. So almost 1 paper per month, so 36 conference papers, some of them in very selective venues, such as USNIX. And as we are open source project, we put something like 100,000 lines of code on GitHub. So now this last slide is basically to introduce the next speaker. So what are the challenges that we had to address in the project? It's very easy to do the introduction, but we had some difficulties to solve, right? So the first one, this is the hardware part. So putting things heterogeneity into the hardware, it's nice, but then you have to provide a unified memory address space, and it's becoming a bit more complicated. Then the software that I've detailed a bit. So how do we conceal the complexity of the hardware platform in order to allow the convergence between big data, HPC, and cloud? And also, I think this is even the most important part in the project is that how do we validate the result? So and we validate, as I mentioned earlier, with 2 ways. So the full-blown pilot application from day 1 up to month 36, and also this proof of concept where we have basically inject 16 different applications to the platform to assess that it's working as we expect and that we are delivering meaningful result to the market. So thanks a lot. And now I let the stage to Nam for the hardware part.
No, I'm sorry, we cannot hear you.
Okay, I'm sorry. There is some technical problems with my. Do you hear me now?
Yes, we do.
Okay, thank you. Sorry again. So I try to go faster in order to catch up the delay. So I will start with the first slides in order to say about the motivation objectives in the design of the hardware for the Evolve platform. So our main motivations is to investigate the integrations of hardware accelerations in order to not in terms of computing, but also in terms of data transfers, and in order to be able to support flexible, scalable, and interoperable exploitations of those hardware accelerators for the benefits of the applications, which is the convergence between the HPC, big data, and AI. And obviously, to validate all our developments on the use case proposed within the projects. So the main technical challenges we have to face in our work is to provide a scalable approach to heterogeneous computing technologies, to make the convergence between the different acceleration software, and also the convergence between HPC, big data, and AI, the expansions of HPC scope to the cloud and edge computing, and all those other stuff, while maintaining the native characteristics of HPCs, which are availabilities, reliabilities, accessibilities, and securities. So I will now detail rapidly all the components of the hardware platform, and starting with the computing technologies and starting with the CPUs. During those 3 years, the CPUs have evolved through different families of CPUs from Intel, both were Haswell and Skylake. And the characteristic is that all those CPUs have in common is they are homogeneous NUMA multi-core CPUs. And the other characteristic from one family to another family is that they vary in terms of cores or frequencies. But the main point is that the performance we can obtain from those CPUs are not only based on those criterions of the cost of frequencies, but also to have taken into account the protocols, the different versions of the protocol of cache currents and memory consistencies, the size of the compute nodes, and the presence or not of node controllers in order to expand the protocols to larger size, and obviously the NUMA factor. And another things to be taken into account in the usage of CPUs in order to obtain the maximums of performance from them is the mixing of different programming models for the CPUs, which are today MPI and OpenMP respectively for the distributed and shared memories. And to do that in an optimal way, we have to take into account the system architectures, other criterions like load balancing, memory management, size of a message, NUMA factors, synchronizations of the message, all the stuff, make it more complex to obtain real optimal performance from the CPUs than just to compile it and using default values. So what would I like to point out in this slide is that today, in fact, the exploitations of the CPUs is still rather suboptimal when we look at the different existing implementations of the applications. The next computing technologies is obviously GPUs, which become very common now in different HPC systems and in our platform. And during those 3 years, we have implemented GPUs varying from NVIDIA K20, P40, and now B100 versions of the GPUs. And as for the CPUs, the performance of those GPUs are computed as factors of the number of cores and frequency. But from our point of view, the main criterions which can have a big influence in the performance obtained from those GPUs, the memory type, its size, boundaries, and repartitions in terms of local memories, in terms of shared memories, in terms of global memories within the GPUs, and also the programming models used in order to program those GPUs from high levels or frameworks like TensorFlow, MATLAB, or low-level programming models like CUDA or OpenCL. Another point which is important also is that how to make the interactions between the GPUs and CPUs more performant as possible by merging between the MPI, OpenMP programming models of the CPUs together with the CUDA and OpenCL, and to make the GPUs usage of the CPU scalable and in terms of mapping of MPI tasks to GPUs, in terms of scaling the code into multiple GPUs and multiplying the GPUs in the heterogeneous cluster. As shown in the figures on the right-hand side, the way that we can merge together different programming models between CPU and GPUs can be set in here in different layers of message passing and shared memories access to each compute node and how use the GPUs within each compute node. The figures on the bottom side is to illustrate how we can optimize the access of the memories from GPUs to GPUs or to the CPUs memories or from GPUs memory directly to the equivalent networks to communicate with other compute nodes. This slide is just here rapidly to illustrate some of our purpose. For example, on the upper left, right side of the slide, you can see some figures, some results obtained from FFT applications. It demonstrates many things. First of all, when we use GPUs, for example, when using CUDA, which is a proprietary programming models against standard programming models like OpenACC, for example, most of the time you obtain better performance than the open standard. It is somehow rather than natural due to the fact that it is a proprietary from NVIDIA. And there's also the performance is some kind of a trade-off between the transfer of data and the executions on the cores of the GPUs. And somehow for this kind of application, we can see that very significant speed up against the CPUs. On the two figures on the bottom of the slides, what is illustrated is that when you combine together the OpenMP together with MPI, we have a very big variations in terms of performance, but also in terms of footprint of the memory. So it depends on what is the criteria we are looking for. We have to, let's say, combine those programming models in a way or another way. Now let's go to the FPGA rapidly. FPGA is a very old technology, so older than GPUs, but it is not yet very well used and considered in the for the applications due to the fact that it deals mainly with hardware considerations. Today, the characterizations of FPGAs are in terms of CLBs, of logical elements, in terms of LUTs, embedded RAM, DSPs, interconnect, or SerDes transceivers, which are not well known by the applications, software applications developers. And the FPGA-based programming models today offer only two alternatives, either directly using HDL like a VHDL or System Verilog, or using OpenCL. And OpenCL, the way of approaching OpenCL with FPGA is illustrated by these figures in here. On one hand side, we have the computations using the software part, and on the other side, the kernels is synthesized and mapped onto the FPGA. And on the right-hand side, we have the stack of all necessary software in order to support these implementations of OpenCL for the FPGA. And what we like to say also is that in terms of FPGA, the FPGA is technologies, is programming technologies compared to the more oriented processors like GPUs, for example. So we have a lot of flexibilities to implement the different features. And one of the features we have intent at the beginning to implement on our approach to FPGAs is to allow it with the abilities to access in a cache coherence and memory consistent to the memories of the CPUs. And this is by using some of the features provided by Intel for their SKU technologies. That means that the abilities to connect the FPGAs directly to the CPUs onto the same sockets using the protocol QPI protocol. And in here, normally, with that, from the FPGAs, we can access directly to the memories of the CPUs in a cache coherence manners. And this FPGA itself can be extended using HSSI connectors to other FPGAs in order to implement larger applications. But after that, Intel's have dropped off this approach. Today, our solutions retain for the Evolve platforms is only the connections between the CPUs and the FPGAs using the standard FPCI Express. But they still remain with the abilities to extend this kind of approach with larger FPGAs, more FPGAs using that other either the directly HSSI or other kind of interconnection between the FPGA. So these figures in here in order to illustrate rapidly how we can interconnect different acceleration technologies together. We have the CPUs communicating through the protocol, coherence protocol, which can connect it to GPUs and FPGA at the same time, so we can combine all those technologies together. Today we have used NVIDIA V100 as GPUs and Stratix 10 as FPGAs in our compute nodes. So now go into the next component of the HPC cluster. There's 3 points I would like to point out from this slide. Is that in our design of the compute nodes, we use these formulas of HPC benchmarks in order to size the memories of the compute nodes in order to be able to fit into different type of applications. That means that 2 GB per core. Another point, as already said by Jean-Thomas previously, is that we introduce the bus buffer exemplified by the DDN's IME technologies in order to accelerate the accelerations from the compute nodes to the storage device. And the third main point is that we also allow to add local storage to compute nodes in order to accelerate some workflows which needs local storage in order instead of going to down all the networks to the storage device.
So Nam, maybe in 2 minutes.
Yes, I will go fast. So the third components of HPC clusters will be the interconnect fabric. And for this interconnect fabric, just to say that for the hardware platform, there's in fact 3 different networks, 2 InfiniBand. First one is to connect compute nodes together. Second one is to compute the compute nodes to the bus buffer and storage device, and Ethernet networks in order to connect the management nodes to the rest of this design. So here is again rapidly the architectures of the platform. We have compute nodes in here. We have a storage device on the right hand side, connecting different bus buffer together with the LUS nodes for the storage. And we have the management nodes to communicate with the outside worlds, connecting together with all the other nodes. So we have all the illustrations on the right hand side. So now I come to the conclusions in order to say it again, what are the main points of our contributions in terms of hardware design to the Evolve platform. We have investigated some aspect of the general purpose computing accelerations, including GPUs and FPGAs, and we also consider the restructuration of the memory storage hierarchy by introducing bus buffer, but also by starting to investigate some other features like data compressions at some nodes. And the main point is that in order to obtain real benefits from these architectures, we have addressed the problems of co-design. That means how to work on application on hand side in order to map it in the most optimal way on those architectures of the platform. Future of the developments will be accelerations, but more oriented to specific applications like AI applications, in situ computations. That means providing computations on some local nodes like storage nodes, for example. Co-designs once again regarding all those new features, new developments, and obviously the evolutions of HPC towards the more open HPC cloud edge continuum. That's all from my side, and I'm now glad to introduce the next speakers, who will be Professor Angelos Bilas from the University of Crete, and who will present now the software part of the Evolve platform. Angelos, it's yours.
Great, thank you very much, Nam. Let me share my screen and the slides. I believe this is it, and you should be able to see in full screen. So my name is Angelos Bilas. I'm with Forth, and I will give an overview of the software stack in Evolve. So Evolve is a project at the crossroads of big data, cloud, and HPC, as was already mentioned. The goal and scope of Evolve has been to process large data sets and to do so interactively for user-facing applications. Now, if I am sort of to give the main and the distinctive feature, right, in each of these 3 words, big data, cloud, and HPC, I would say that big data has always been about productivity. The goal has been to decouple users from the platform and allow them to process a lot of data with reduced effort. The cloud has always been about optimizing resource cost. It has been driven by consolidation, resource provisioning, shared use of resources that ultimately aim to reduce cost. And HPC has always been about performance, striving for vertical integration and using advanced storage interconnects and accelerators. So the hardware platform in Evolve has HPC features, as was discussed in Nam's presentation. And for the purpose of the software stack, we can sort of abstract this platform with the following aspects. It has substantial heterogeneity. It is of substantial size, hundreds of threads in large multiple servers and substantial memory. It uses fast interconnect InfiniBand, in fact, with RDMA support, and then different generations and types of accelerators, both GPUs and FPGAs. And I'm not sure, maybe, okay, this is great. On the storage side as well, there is substantial heterogeneity. There is the Infinity Memory Engine, which is used as a burst buffer. This is high throughput storage. There is local storage devices that offer high IOPS, and then there is external archival storage for end results. So I will now go over the software stack in two parts, the front end and the back end. The front end of Evolve is basically, we place this under an Evolve dashboard, which is the front end for all users in the platform. The goal is to decouple users from the complexity of the hardware and the software, the underlying hardware and software stack. It offers secure and private user management via isolated namespaces. It integrates all Evolve and third-party services, and this is done with a container-based management sort of approach, which has proven very fruitful. It has been significant integration effort to provide this dashboard, but in the end, as we have seen from applications and proof of concepts, this effort has paid significant results. The main abstraction offered by the front end is a notebook abstraction, where users, they can essentially provide, they can program their own workflows. We chose Zeppelin for this purpose, but they can also make extensive use of shared templates. The platform includes a custom interpreter for workflows, but you can find more about this in deliverables and publications, right? I'm not going to sort of discuss this in more detail. Evolve workflows in the project, in the end, they are an end-to-end synthetic description of computation for us. Workflows are important for two reasons. It is what the users care about. Users, they want generally to describe an end-to-end process, and they care more about, getting the whole result in the end rather than focusing on a single stage. But also workflows are important for the system because it allows more room to optimize execution, because the system has an end-to-end view of what it needs to do. Figuratively, a workflow in Evolve looks something like this. Initially, you may want to open a data set, then you perform some pre-processing on this data set. Afterwards, you may train a model based on the data, then you perform a simulation of some phenomenon, right, using, let's say, an HPC stage. And then in the end, you post-process the results. And finally, you may want to use visualization to sort of summarize the results to the user. Now, one distinctive feature in Evolve with respect to workflows is that it allows integrating HPC tasks and big data tasks in a single workflow. So workflows can use MPI stages. MPI can also be used interactively from notebooks in Evolve. MPI tasks are able to use GPUs and InfiniBand via containers. So we have extended containers for this purpose. And then Evolve automatically creates the environment where it will execute these MPI tasks. We call this virtual cluster, this environment. It allocates resources to each MPI task along with big data tasks, and I will say a little bit about this later on. And then cooperatively, it executes the MPI tasks under Slarm and Kubernetes. And again, I will say a few things about this later on. Finally, the front end includes extensive vertical monitoring in the sense that it provides information about hardware resources, the software stack, and storage I/O, which has been a focus for us. And these monitoring aspects in such a complex platform are extremely important so that both, let's say, the system side and the user side, they can have a view of what is happening in the system. Let me now move to the back end of Evolve. This is mainly the part of the system that is responsible for using the available resources and achieving high efficiency. So the backend in Evolve has, let's say, three main aspects. One is end-to-end integration of microservices with the HPC platform. These microservices, as examples, the microservices include Kafka, Spark, Spark Streaming, TensorFlow, and Keras, MPI, and extensive visualization support. There has been quite a bit of effort in integrating these microservices in the platform and making them available to applications. However, for now, I will consider that these are given, they are running in the platform, and I will focus on the next two aspects of the system. The next one is enhanced storage features and quite advanced resource management. So with respect to storage, Evolve offers a unified storage layer. Storage is important in Evolve because all tasks and jobs communicate with each other via storage. So essentially communication happens via storage-based address space, which offers practically unlimited address space, and datasets can grow significantly. The unified storage layer contains a component DataSim, which was again mentioned earlier, and this abstracts data as data sets. This is, let's say, a control aspect of the backend, where users see names for data sets without having to worry about where this data are stored or what their format is. And they are visible everywhere in the system and throughout the lifetime of jobs across both tasks and nodes in the platform. The second aspect of the unified storage layer is a device-independent method to access data. This is H3, it's a data access layer, and it offers access to data whether they are stored in local devices, shared storage, or even archival storage. The idea is that H3 provides applications, tasks, and workflows the ability to store transient results on fast local storage, and also persistent end results, let's say, to archival storage, such as Lustre. Moving forward, the resource allocation in Evolve is based on microservices, containers, and Kubernetes, which has proven a very fruitful approach. There are two distinguished and quite advanced features. One is that Evolve performs mixed resource allocation for HPC and big data tasks, workloads, and also users can request information, let's say, performance target that rather than requesting only specific resources. So workflows, executing workflows within in Evolve, this happens in a cooperative scheme under Kubernetes and Slarm. In our approach, Kubernetes is used as the master, although other approaches do exist. So Kubernetes has a full view and of resource allocation in the system. We can support executing full Slarm scripts as an MPI job, so this is pretty generic. The users can issue tasks to the system as complete Slarm scripts. Then Kubernetes creates the virtual environments for executing each of these tasks and starts a Slarm subsystem, a Slarm in the virtual cluster, and the two of them, Slarm and Kubernetes, cooperate for allocating the actual resources. We have been executing mixed HPC and big data workloads over the last few months, and the results are indeed quite interesting. About resource allocation, the second significant aspect is that Evolve automatically allocates resources in the following sense. Big data workloads tend to be elastic, and despite this fact, users today need to determine the resources that will be allocated to each task in the system. This is very challenging for users, and it leads to over-provisioning. Evolve instead asks users to specify a performance target, for instance, target throughput. Then after that, the system takes care of resource allocation, so it maps the performance to required resources, allocates these resources and adjusts them at runtime. And this is sort of implemented in the system as a custom scheduler within Kubernetes. This adjustment now of resources is based on an online performance model that our scheduler builds for every application. This model or the approach that we use is agnostic to the application type. And in fact, it can even cope with multiple resource types, CPU, memory, and IO as well. So having provided the information about the front end and the back end, right? If this sounds interesting, please go ahead and try out the platform. There are different ways to do this. So we have get in touch because we have started already to discuss deployment of the platform in specific applications. One of them is satellite image processing, where there is significant need both for data storage, right, and computation. There's a possibility to access the combined hardware and software platform at Atos for third parties. So if this is interesting, again, please get in touch. The platform is available as a cloud version, which you can download and use either on a public or a private cloud. However, this version of the platform does not include the hardware, the HPC hardware support features, because these are not generic features that you can find everywhere. And finally, most components in the platform are already available as open components. So you can download them and try to integrate them in your own platform or even extend them. And in any case, anywhere we can offer help, we are more than glad to help with the platform. Thank you very much for your attention. I'd be happy to answer any questions now at the end of this session or even later on via email. Nam, the floor is back to you.
Thank you very much, Angelos. So I will introduce the next speaker, who will be Vasilis Spitadakis. Vasilis is R&D manager from Neurocom, and Vasilis will present now the different use case of the Evolve project. Vasilis, the floor is yours.
Thank you, Nam. Hello, everybody. I will present you briefly the 7 use cases that were adapted into the Evolve platform and their main achievements through this adaptation. As already mentioned, we have 7 use cases, 7 real business case scenarios from different areas. First has to do with change detection satellite images, maritime surveillance, optimizing agro production yield, predictive maintenance for vehicles and public transport operations planning, data-driven vehicle engineering process, and demand mobility services. All these use cases are using the same platform, the same cluster, exploiting various different microservices, each one to satisfy its different, its diverse requirements in terms of volumes, in terms of rates, in terms of calculations. So the main goal out of this adaptation was, of course, performance. But apart from it, apart from this, we wanted and we identified flexibility that is necessary in order to conclude such adaptation that is necessary to move a conventional, let's say, application to a new era where you need to exploit HPC, you need to exploit big data frameworks, you need to move things up to the cloud. The main work that has been focused, that has been made throughout this adaptation is containerization of calculations, parallelization, scheduling, and visualization. So we utilized Kafka for data ingest microservices, TensorFlow. We utilized GPUs, MPI, Dask for scheduling, Spark streaming for stream processing, and at the visualization stage, we had also the Web Lizard technology component which was integrated also within Evolve. Let's start with the change detection application. It is an Earth observatory application where you need to get images from the same area at consecutive time windows, let's say, which need to be compared. And finally, you need to identify and produce a new map, a new image that identifies the changes that are being observed. So it's a very interesting and very important application nowadays, because many different applications and business domains are relying on change detection. And such kind of multi-temporal change detection is needing fast access storage for a big amount of data, and computational intensive processing in order to identify these changes, and in order to be able to be able to process larger areas in more quickly. So for Thales Alenia, which is actually the business owner, the objective of this pilot consisted in detecting changes over the entire Europe during 1 year, with a revisit period of 10 days. So this application required to access and process about 35,000 tiles, which is about 20 terabytes of storage of data coming from Sentinel-2. The main steps were including the downloading of Sentinel data, of the Sentinel data product from the Copernicus Access platform, processing each Sentinel data product in a single image with a bunch of interest, and finally having 2 time consecutive images of the same field of view being generated. The last step is to compute the change detection map between these two. So what we did, what Thales Alenia did, it utilized parallelization frameworks, the stream analytic engine, fast storage, and hardware accelerators in order to automate, optimize, and boost the performance of the change detection tool. Actually, for this use case, we also explored different variations of the platform, using also the task scheduler, which has been deployed for parallel computing inside the modules. And the module with the artificial intelligence algorithm has been rewritten in pure TensorFlow to take advantage of the GPU accelerators, as well as it was ported using OpenCL to FPGAs, so that to compare the performance using the HPC features of the platform. All stages were containerized. Communication was done using Kafka topics. And finally, we made experiments with 8 different variations of the platform, and we experienced 10 times faster average time for generation of one change detection map from a couple of Sentinel-2 images running on CPU and Dask. While when we brought also the GPU, we moved from 10 times faster to 15 times faster. And what was actually more interesting for us and for Thales Alenia is that we experimented on a big data environment where we work with 200 Sentinel-2 images, where we get using the CPU, not the GPU, but the Dask version of the platform, of the setup, we got 120 times faster conclusion of the whole process. More information can be got from Thales Alenia about this use case. We can move on to the next use case, which is about maritime surveillance, a very important application for maritime safety from transport, for monitoring and identifying illegal immigration. Here, the business owner is SpaceLAS, a company from Greece. And the stages here of the processing are including data acquisition of 2 different types of images. The first one is getting images for SAR, radar images, monitoring the seas, as well as getting data from the AIS system for the automatic identification system of vessels. And you need to correlate these two in order to identify whether there are some abnormal, let's say, moves. And so we have data acquisition from these 2 sources, anomaly detection run on the AIS data, image filtering and processing of the radar images, vessel detection, and fusion correlation between these 2 sources, and finally, visualization over a map GIS interface. All stages were deployed in the platform. They utilized the Zeppelin, the Volt-specific Zeppelin notebook facility. And the main work was to transform the existing pipeline to the Evolve logic, which included the engineering of the workflow and containerization of all stages, with the aim of taking advantage of the accelerations, of the Evolve accelerations, mainly the parallelization for the IME fast storage facility and the hardware accelerated distributed processing. Dedicated data station modules were developed for both the AIS data and the radar images, and all the processing stage was achieved natively within Zeppelin. Having evaluated the deployment in Evolve, we got out vessel detection time we reduced the time for vessel detection by 70%. 89% for anomaly detection we reduced the anomaly detection, the training time of the anomaly detection model data. The accuracy has increased by 5%, while we managed to increase the time spatial window, which is very important in order to be quickly into responding into such requests for monitoring a specific area. Comparing with the previous situation, in absolute numbers, this means for vessel detection now we can do it in less than 1 second, while before Evolve we were doing it in about 3 to 4 minutes. Anomaly detection was needing 8 hours to train the model. Now 2 hours are more than enough for the training phase. Data-driven vehicle support is another use case. Here we are mainly dealing, this is a computational intensive application that it is mainly executing time series analysis for anomaly detection over a time series data, which are monitoring the data, the pressure of a cylinder in an engine, which combined with other engine operation data can identify areas, points in time where abnormal situations need to be considered. So we have to find patterns and correlate them to numerous other patterns that characterize normal behaviors, so that a specific pattern can be classified as normal or problematic. AVL from Austria is the business owner here. They have already a system doing this called EPOS, working with the cylinder data, very well optimized for the environment in Windows. AVL managed to reduce by 40 to 50% the overall workflow execution time. The main work that has been done was, okay, they containerized and uploaded it to the Evolve platform. They use profiling in order to optimize the code. They changed the file format to Parquet, which allowed to take advantage of parallelization. So it was mainly the parallelization that pushed it, that was exploited, while the experimentation with the GPU didn't reveal so great performance improvement, because actually it was applied to a specific processing stage which was consuming just 1% of the overall calculation time. Public transport the public transport operations of Thieme, a Toscan a bus operator in the area of Toscana in Italy, brought their data into the Evolve platform. Their data was mainly about bus events, schedules, and the network, the actual network. And we implemented 2 different workflows. One was a batch workflow dealing with getting data about the actual performance that is monitored over the transport network, and comparing it to the schedule, to the promised, let's say, operation, which is a very important decision support tool for the operation of the authority. The need there was to expand, to make the queries more, to make the queries faster, and to expand the time window where you base such decision. And the second workflow was a real-time workflow, which was not existed before. And now it made possible, it was possible through the Evolve platform. Both workflows utilize the Kafka ingest microservice. They utilize the Argo events for scheduling, and Spark, as well as Spark streaming for the real-time case. Two different visualization stages were exploited. In the batch workflow, we integrate their existing business intelligence application through the Spark Thrift server, so that to exploit the Spark query engine results and visualize them on the existing application. While for the real-time workflow, where you need to identify congestion, the congestion on the network at the time it happens and correlate it with the bus event data that we are getting, we utilized the visualization component that is being integrated within the Evolve platform with the Web Lizard technology. Here we got also important, very useful, very good performance results. Mainly, there are some daily queries which are applying on a daily basis within a period of interest for 30, 60, 90 days of service, where you need to get a summary of the transit time analysis. And this query gets from 2 minutes up to half an hour when you are making this query of over 90 days. Now we need just a few seconds, 60 seconds for 90 days and 11 seconds for 30 days to get this query done. Very important achievement is that before Evolve, the operator was working with 1 month data in order to take decisions, data from 220 bus seats. Now, 1 year data can be processed across the whole area of Toscan. And last but not least, okay, we didn't have any past experience from real-time visualization from the network, but now we got, and actually now we have the experience through Evolve, and now we can be able to visualize 2 or 3 selected lines of routes within 6 seconds, as well as we can process more than 20,000 arcs in the transport network in under 20 seconds. Another application has to do with active production optimization. This is very important.
Please, 1 minute. 1 minute.
This has to do with the monitoring of agriculture parcels, where you need to identify the crops cultivated, and you need also to simulate the growth in respect to the climate and environment and the farming practices that are being applied, as well as the environment conditions. This is a very demanding application dealing with numerical processing, with vast data of numerical processing with and great complexity. Here we utilized MPI, especially for the simulation process. Everything again was containerized, and we managed to get an increase of from 90% to 97% in respect to the success rate of crop detection. While the most important achievement is that we Cipetec, which is the business owner, managed to multiply the dataset size, the area, by 5 times. Predictive maintenance is another use case, another business case. Here, here we got again data, engine data from vehicles, which data from warranty repairs with current vehicle sensor data. Here again we used R, Python, TensorFlow, and MongoDB. We apply logistic regression, linear discriminant analysis, classification regression trees, and SVM. And finally, we got a speed up of within 2 and 3 times speed up in the overall preparation, training, and serving of these data models. We are also now measuring the speed up with using the GPUs. Finally, we have the demand mobility services, the business case of BMW, where we have the problem of ride hailing. So you have a network of a share of cars that are within a city, and you have requests coming from people who want to move from one place to the other, and you need to optimize the way to which car will serve which request and at which time. The business case actually has to do with the research that BMW is doing on the various algorithms. So with Evolve, all these simulations were done over a larger amount of data sets that were actually covering the New York, let's say, taxis, the fleet of taxis, and we got significant acceleration as well as significant increase of the problem size that is being investigated. To conclude, we were expecting that we were expecting remarkable performance improvement because for most of the use cases we are moving to parallelization, we are moving to GPUs, we are moving calculations to FPGAs, to efficient storage and efficient compressions and efficient visualization. However, I stress again that the most important achievement, the most important conclusion out of these experiments was that use cases managed to increase the quality and quantity of business indications, larger areas, more accurate results, while on the same time they got development efficiency. Experimenting with HPC, with different components of the platform was now more easy. The dashboard, the Zeppelin notebook, or all these scheduling tools and upon the containerized stages of calculations made their life easier to our new data pipelines, quicker data pipelines, and easier to manage them and edit them and re-engineer them. Thank you for your attendance, and I will pass now the floor to Alexander, who can tell us about the proof of concepts, which were, let's say, some more use cases that were added into our experiments.
Okay, thank you very much, Vasilis. I introduce rapidly Alexander. Alexander Stokers is a project manager at Virtual Vehicle Research GmbH, and he will present to us now the proof of concept for the Evolve project. Alex, it's your turn now.
Thank you very much, Nam. I'm trying to share my screen. So I hope you can see my screen now.
Yes.
Yes.
Well, you have already seen from Vasilis 7 official project use cases that have been implemented in the project runtime. I would like to now draw your interest on our proof of concept experimentation or implementations. You can see proof of concepts somehow as a smaller mini use case that were identified during the project and involved also externals that can be external partners like external companies that implemented workflows on the testbed using the support of the consortium partners, but can also be partners from the consortium members, but external to the core team that implemented workflows. In proof of concepts, you can have two variations. The first is a variation in data sets, so different data sets than in the pilots, but also a variation in the application context, so different application context. We have in total implemented 16 POCs on the testbed, and you have on my slides, there is a list of POCs. I won't go into detail in all of them. Don't worry, that we would need much more time for this, but I would like just to give you some overview on the application context. So we have a POC on vehicle monitoring, but also on sensor measurements. But we then also have other application domains like genetics or genotype imputation. So biology also as an application domain that was addressed in POCs by Forth. We have further image processing POCs. We have for the bus service use case that you have seen, we have also two POCs. One is on a bus fleet monitoring from a different city, and the other one is on traffic congestion, but also using data from a different city to show the generalizability of the workflows that have been developed. We have one POC also in the domain of retail and retail AI. This is especially really cool because the implementation here was done by an external company, by a French startup, XXII. They do in-shop monitoring using neural networks, and this was done together with DDN, but most of the implementation they really did by themselves, which is super cool for a European research project, I would say. We have two more POCs on crop grape simulation and also on the recognition of field boundaries for crop fields. We have, so here in agriculture POCs, we have POCs on network security analysis, so cyber security, security incident detection. We have DNA, RNA sequencing, we have particle simulation, so we also address physics as a domain. And we also have another application-oriented POC working on telecom usage data to predict churn. Finally, to finalize with the list of POCs, we have one of driver monitoring, which I would like to go into a little bit more detail, and another one on object detection for automated driving for autonomous vehicle, which is a very up-to-date topic, I would say. I would like to go a little bit into detail in two POCs that were implemented. The first POC I would like to talk about is the status detection of vehicle assistance systems, of autonomous driving systems from video streams of a vehicle dashboard, which is really nice. Why is this useful at all? This is useful when you want to do user experience studies or user experience studies, putting people into an automated vehicle and assess how they interact with the car. I have here a screenshot. This is more or less an image of a vehicle dashboard of such an automated vehicle. In this case, it's from Volkswagen, and you see here some green symbols. The first symbol showing a road. This is green. That means the vehicle was able to identify the road borders and can steer autonomously, so to say. And the right symbols, this is also green. That means the vehicle was able to identify the distance to a vehicle driving in front of it. That would be this yellow symbol. And if you have both activated, you have some feeling of automated driving. So in a driver study, usually you would like to know when the drivers have activated the systems and when the systems work properly, which is not very easy because you do not usually get access to the vehicle campus, to the CPU to get this information automatically. So there is some kind of hack needed, and this hack is recording images of the dashboards with a camera and then applying some sort of image recognition, computer vision technologies to identify the status changes in these images. This is more or less what was done in the proof of concept. So here also, like in the pilots, there was a workflow implemented on Evolve for the detection of the symbol states. It was not machine learning, it was a pattern matching approach. You see here this pattern. So it was explored where this pattern emerged in this video. Of course, there were some tunings like applying GLAI for contrast adaptation to improve the quality of this pattern matching approaches. And the workflow was implemented using OpenCV and using also GPU and CPUs and GPUs. The workflow also used Kubernetes, so Argo. There's the Argo file. It was a directed acyclic graph. So you see here the parallelization of image processing to speed up the performance. This is a video. So you see here this dashboard of a vehicle. It's exactly a driver is using it and it's driving. And you see here a little bit also there are light effects. And you see here the small videos. And in the subtitle file that is loaded to the video, and this is automatically created, you see here a change from the status in use, activated in use, car in front, and activated in use. So it detected really the symbols correctly. You see here also the screen card, the user interface of Kubernetes, and you see this was done in parallel, the processing to speed up the processing time. So more or less, we experienced, so from porting this workflow from the local environment, from the data science, from the PC of the data scientist, the desktop PC to the Evolve platform, you see here the impressive performance improve 41 times faster when using the GPU and the CPU and the GPU instances in parallel. A second POC I would like to go a bit more into detail is driver distraction, so driver monitoring. You probably know that distracted driving is one of the most common causes for serious road accidents, and this to prevent these road accidents, the driver monitoring systems are needed. And in this proof of concept, the idea was to develop a lightweight driver monitoring solution running on a smartphone of the driver and processing videos, detecting distracted driving on the images, and then warn the driver. So here there are 3 examples of the data set that was used that show distracted driving behavior. So here the driver is like texting with the phone. Here the driver is reaching behind, and here the driver is talking. So these are really examples that were used. And the data set used with all these labeled images was from a challenge on Kaggle. It was the State Farm distracted driving data set. So State Farm is a US insurance company that posted this data set on the Kaggle platform for a challenge. And the data set was used in Evolve really also to train, first of all, a machine learning model that is capable for detecting this distraction classes. So you have 10 classes of distraction on the right side that are in the data set, and also then to deploy this model on a smartphone for having some lightweight driver monitoring system. The data size was for the labeled training data set about 950 megabyte of images, and for the test images more than 3 gigabyte for them 3 gigabyte of image data. Also, I won't go much into detail, but also there was a pre-processing conducted to pre-process the images before finally the action was predicted. The training was done in first in single mode, so without any acceleration on the Evolve platform, using Zeppelin notebook GPU and OpenCV, the Python library for training the machine learning model, but was then later to speed up the performance also done in a distributed way using Qbox, but also MPI or TensorFlow, more specifically the Horobot framework, which was provided as a service on the platform. This is a framework developed originally by Uber, used for such image classification challenges. Finally, as in the first POC, I think here also the implementers experienced really a huge performance increase in training the neural network, the machine learning model. It's about 15 times faster than in the local environment, but also for predicting the action, so running the model to identify a typical distraction on an image. It's also more than 7 times faster than on the local environment. The accuracy is also pretty good. So overall, there was an accuracy of 98, even more than 98% of identifying the distractions here by using a base model from the literature, but that was not very optimized. That was adapted just to test the Evolve implementation. Maybe for some who are interested, what was the most difficult class to identify? That was obviously here makeup. That was the hardest type to classify for the neural network. And there was a lot of confusion, as you can see in the confusion matrix of this class, with 2 classes: talking to passengers, texting right, and drinking. Finally, when you remember, the overall goal was to really have a driver distraction and detection and warning system. So I've talked a bit about the distraction, but not about the warning. So to also have this, my colleague who did this implementation deployed the TensorFlow Lite model on a smartphone, and to run it on the smartphone with the front camera, and also tested this in a small scale study in a real world setting. And of course, as you probably might also figure out, there is, of course, when you do it in the real world study, there is a much lower reliability of the system due to different camera angles when you have it in the car, and also different light position or light and light effects. So it might obviously need a more, even more comprehensive data set with more different situation to train a very sophisticated model. But that was obviously not the goal of this POC. The goal was really to challenge the Evolve testbed and use as many of the Evolve microservices that are provided as possible. And I think that went pretty fine. So that's it for my talk. I tried to save some time. I hope it was successful, and I'm looking forward to your questions.
Okay, so thank you very much, Alex, and thank you to all speakers of these sessions, Jean-Thomas, Alex, Vasilis, and Angelos. So it's now time to open to questions. Is there any questions from the audience? Okay, so if there is no question from the audience, I suggest something to wrap up our sessions. We have about a little bit more than 6-7 minutes. In my presentations, I already start to say for the hardware design aspect of our Evolve platform, what will be the next step we envision on outside in order to make all things evolve, and particularly for the design of the future architecture for HPC. So I already sketched about implementing more the hardware accelerations, more specific and AI-oriented hardware accelerations, more institute computing, and particularly storage, in storage computing, but also in networks computing. I also talk about more works about the co-design in order to adapt applications to those new features of hardware architectures. And more than this, afterward, to adapt HPC architectures in order to support more efficiently the overall architectures of continuums of cloud and edge computing. So this is the visions on the side of the hardware. I would like to know about your visions on the different other side, on the software side with Angelos, and also you see on application side together with Vasilis and Alex. And at the end, Jean-Thomas, maybe you can wrap up overviews of the project. So suggest Angelos, you go next.
Very good. Thank you, Nam. So as a reflection in the project, right? The building the software stack has been extremely interesting, and in the end, it was also it paid, right? And the applications were able to use it. One of the things that we have started wondering about is how do we extend this to the edge? So the full platform in Evolve right now is for a platform within the data center, for a hardware setup within the data center. But many of the applications do require, especially new applications, using the edge. And some of the concepts, workflows, managing storage, state, right? These are problems that Evolve does solve, but addressing them for the edge, they introduce significant new challenges. And we believe that this is going to be a next problem for us, and somehow we will need to go in that direction.
Okay, just interrupt before the continue with Vasilis and Lisa. There is a question from the audience. The question is how Evolve can be used for dynamic system simulations such as climate or other complex problems. So who would like to answer these questions? I can try first. From the hardware part, obviously, hardware part, when we try to introduce hardware accelerations to our HPC architectures, it is effectively to support the simulations of more complex problems, to be able to handle larger problems, to provide the ability to process the simulations in more parallel way, to access it, and afterward to use a more approach, different kind of approach also to the simulations problems. For example, using AI-based techniques to the simulation problems. So that's why what we are doing in Evolve somehow is not only oriented toward AI applications as maybe giving this kind of feeling during the presentation of different applications, but also to serve also the simulations of complex problems. So, and we continue to work on this in order to provide more abilities to communicate between different computing technologies in order to be able to execute more efficiently different simulations workflows to include the different aspects of simulations, visualizations, debugging, stuff like that. So this is for my part. Who else can add to this answer to this question? Thomas, Angelos, Alex, or Vasilis?
So now I can say, so basically for an application that is coming from the HPC world, right, the hope would be that by using the platform, someone will manage to improve, let's say, productivity. So if you have an end-to-end workflow that describes what you need to do, without too much effort, it should be possible to execute this on the platform, and this should make modifying the whole workflow easier for users, so they can experiment with it, they can create alternatives of the workflow, and we have seen this in some cases in the use cases as well in the project. So coming again from an application, right, that is, or from a workflow that is, let's say, HPC oriented, the bigger gain would be on the productivity side, I think, right?
Thank you, Angelos. Anything else from all that?
I would say now, just to wrap up also in respect to the use cases in general. Well, having dealt with all these different use cases and proof of concepts, we realized that for all of them, now it is very productive how the final results that they're getting, and in terms of performance, and it's very productive now of what they can do onwards with these workflows, because requirements will still grow for them. So one thing is this. Now, concerning their move, starting from the before Evolve situation to the getting on board Evolve, the effort might be different from case to case, because not all use cases are let's say, have already reached an architecture which is very close to a workflow logic. So it is very important that for a use case like the one mentioned in the question, like climate simulation of dynamic system simulation of climate conditions, as long as there is a workflow of specific calculation stages with different data sets from state to state, using using some microservices, this makes easier their move onto the Evolve platform and the quick exploiting of the benefits that the platform brings. So this is so to my view, use cases like the one mentioned in the question can be utilized, can be brought on Evolve, and especially dealing with large amounts of data with AI techniques and similar calculations. But it is good it will be more productive if they are already, if they have already structured into workflow-like approach their use case.
Okay, thank you very much, Vasilis. So there is not much time left. So I suggest that Alex, you have 1 minute, and afterward give 1 minute to Jean-Thomas to wrap up the session. Alex, he has something to say.
Yeah, so looking back to the implementation of the POCs, I think it went quite smoothly. So we were able to identify more POCs than we planned, which is not something that I have seen often in European research projects. Especially our POCs, we had like 4 POCs. We really have this workflow logic that Vasilis mentioned. So for us, really moving them to Evolve was not or just used a limited deployment work, which was fine because then we had more time for testing and improving the algorithms.
Okay, so there is 1 minute left. Jean-Thomas, the floor is yours to wrap up for the project. Jean-Thomas.
Okay, sure. Okay, so just in 1 minute, I think in Evolve we've been pretty successful about optimizing things within the data center. And as you've mentioned, now we have the feelings that, I mean, we're already seeing this trend that it's not cloud, it's multi-cloud. So organizations tend to have their computation data distributed. And then with the edge, it's even more striking. So we see this movement toward, data anywhere where there is data acquisition, and compute everywhere. You move the process close to the data acquisition place. We really see this as the next frontier for Evolve-like project. Within the data center, now we are safe. It's running well.
Thank you very much, Jean-Thomas, for these conclusions. Thank you again, all the presenters for your contributions. Thank you for the audience for your attendance, and I suggest you can join us on the booth if you want to have further discussion together with the partners of the project. And thank you also, obviously, to the organizers of these sessions, Mattia and Petra. Thank you for your help. Bye. Bye-bye. Bye.
Thank you. Bye-bye.
Good morning to all. My name is Fabio Oliveira. I am the communication consultant at Zenith Wings, and I will be the moderator of this session. Zenith Wings is proud to showcase right now two of its main research and development projects during this online session, the European Big Data Value Forum 2021, Operator and Smart AgriShare. Starting our session, let's meet Zenith Wings. It's a Portuguese high-tech company focused on research and development activities, providing innovative solutions for various fields, such as precision farming and Industry 4.0. Our portfolio includes integrated Internet of Things solutions to improve the quality of agriculture and to increase farms production and product tracking solutions in industrial distribution system. So, welcome to session Enhancing the Power of Data in Industrial Environments by Zenith Wings, showcasing of ongoing research and development projects. And welcome to our speakers, Eva Rodrigues, Delivery Manager at Zenith Wings, Carlos Oliveira, Head of Product at Zenith Wings, and Duarte Folgado, Scientist at Fraunhofer, Portugal. The first session, how data can be used to improve working conditions in manufacturing. Eva and Duarte, your turn. Eva, please turn on your microphone.
Yeah, okay. Thank you, Fabio. So we are going to see how data can be used to improve working conditions in manufacturing. So you can pass to the next slide. Yeah, regarding the project operator. Next. So we're going to do a showcase of the project operator. Regarding the problem, manufacturing industries and services are the motor of European economy, currently securing 50 million direct jobs. The industrial and service sector in Portugal employs around 23% of active workers, which makes it a highly relevant sector for the national economy. To ensure competitiveness, there is an increasing demand for digital transformation in manufacturing, and the current approach is mainly centered on productivity and also considering some ergonomics aspects, but not addressing cognition at all. So systems developed for this purpose need to be flexible to assist the shift from mass production to mass customization, but always keeping workers, their productivity, job satisfaction, and health at the center, so that digital transformation enables sustainable operations. The challenge here is to develop the technology frameworks which combine ubiquitous human movement tracking with worker self-reported endpoints for a holistic digital twin representation of shop floors. The framework will deliver metrics which can offer a means for faster, accurate, and ubiquitous digitalization of work study, and offer a means for self-reporting to digitalize the assessment of job quality indices through personal and ubiquitous technologies designed with the N for the operator 4.0. Yeah, so the objective in Project Operator is to develop tools for risk exposure data analysis in the workplace, building on the concepts of positive ergonomics, Operator 4.0, and on the job quality indices by the Eurofund. By collecting and visualizing data on aspects such as physical environment, work intensity, working time, social environment, or skills and distraction. So we are going to tackle Industry 4.0 workplace holistically by gathering and crossing quantitative and qualitative data by the worker's point of view. So we get a richer picture of the worker's well-being, enabling better predictive models. We were going to continuously validate our developed solutions and build large data sets through continuous field work, ranging from short contact sessions during technical development to long-term trials enabling impact assessment. Our vision to this project is to establish a more balanced approach for cognition, productivity, and ergonomics perspectives. The three perspectives before and after project implementation that we can see on the left image, the before, and the right image, the after the project implementation. We have now two use cases from the two most important industries in Portugal. They are both facing increasing competition from emerging markets, while the workforce is generally getting older, and they are both interested in exploring new ways to differentiate from the competition through product and through process. We have NSAT Apparel that is focused on textile and clothing, and we have also Volkswagen Auto Europa that is focused in automotive. Yeah, you can pass now, Fabio. Now my colleague Duarte Folgado is going to present the using wearable technology to support operators and digital transformation. Thank you.
Okay, thank you, Eva. So now that Eva just make an initial introduction, we'll delve into more technical details about how we are leveraging the wearable technology to support the operators and the digital transformation at the workplaces. So the first thing that I would like to point out is regarding the digitalization of the work study and the ergonomic risk assessments that nowadays are conducted on large industrial lines. So in large industrial plant, in the shop floor environments, the movements that the operators accomplish during the working day are pre-established according to a set of timings, a set of methods that are actually well known about the industry. And there is a discipline regarding work study, which is conducted systematic examination of the methods of these operators are conducting to pursue an effective resources and standards for performance of the activities carried out. Nowadays, work study is accomplished via observational approach, where usually there is a person that is near the operator and timing the movements manually in case of the work studies and the productivity departments. In case of the ergonomic departments, usually across all the databases to complement databases information about ergonomic movements. Usually there is also an ergonomist at the workplace to evaluate the angles and the postures that the person is doing and to conduct an evaluation. In order to have a more streamlined approach and to offer tool to these end users, we ask about how can we use wearable data collection and data-driven methodologies to contribute towards the digitalization of the work study. So we drafted an initial protocol of what about will be the day of an operating wearing this set of technologies. So, and we started to make an assumption and starting to make some guidelines to take some technologies for cognition, such as the FNIRs, for the productivity inertial sensors and the ergonomics inertial sensors and physiological information. And in case of the productivity, we are using an inertial sensor that collects data like from the accelerometer, the gyroscope, and the magnetometer to have the information about the movement of the operator. With this information, our KPIs will be the number of cycles, the production rates, the similarity with even a standard method that is accomplished by a highly skilled operator that established how the operator must do the method, and then we'll compare these methods with the other operators that are accomplishing the same workstation. This information can also lead to the number of unplanned stops that might occur during the working shift. In terms of the cognition, we are able also to perceive the workload about the subject regarding in a particular task. And in the ergonomics, we are using more sensors to have a more redefined view about the upper body posture of the person. In particular, we are using 7 inertial sensors to get angular data from the upper body of the operator. And this is accomplished with the inertial sensors, and we are also pursuing some studies, in particular without the physiological parameters, with the ECG and electromyography. These are examples of the sensors that then the prototypes that we are produced during the projects. Starting from left to right, on left, we have a self-report hardware that collects information more with regards with the mental states of the person, in particular if the person is feeling pain, if he's feeling support, and enables to have a more richer view with regards to the cognition and the mental state of the person. In the center, we have the prototype for the environmental, where we can sense the temperature, humidity, luminosity about the workstation to correlate those variables and create a richer picture about the operator. On the right, we have the setup for the ergonomics and productivity, where we can see a box, a casing near the hand that contains the inertial sensor that retrieves information about the motion of the operator. And in this case, it is embedded with the glove that we are also prototyping. This is a more complete view of the setup of the ergonomic system. So to monitor ergonomics, one sensor will not have information that will be requested to have a more complete view of the operator. So we scale to a complete set of 7 sensors to give a more rich view of the upper body posture of the operator. And now I will speak a little bit about the algorithms that we are doing. So as you can see on the very top left of the slide, we have work cycle segmentation. And in this case, we use a neural networks approach. And then on the bottom, you can see the data. And then this is what is data of the operator in motion. Since the operator does accomplish the work cycles repetitively during his working day, the data that we have will be also repetitive. So we can see that we have a repetitive trend of the data that we collect. Again, the accelerometer, the gyroscope, and the magnetometer. And the goal is to identify the instance where on that data that corresponds to the end of a given work cycle, and then, of course, to the start of another one. If we can accomplish that with the segmentation, then we can leverage those information to extract the KPIs that I've defined previously, such as the number of items and even the productivity of the operator. And on the bottom of the figure, you can see the results about the neural network segmentation that we're using, which is correctly identifying where the cycles begin and where the cycles end after the algorithm learned with a data set. With regards to the ergonomic risk assessment algorithm, so we are using a setup composed of several sensors, like I mentioned, which is able to give angular data from the trunk, shoulder, elbow, and wrists. And then we are using 2 guidelines for ergonomic risk assessment. One is the ISO norm 11226. As you can see, in particular with the several anatomical positions or the several anatomical joints that we have, it designs and scores positions of low, medium, and high ergonomic risk exposure. And then since we have the angular that is being tracked across the inertial sensors, then we compare across the ISO standards to see whether or not a person actually is spending a lot of time in, let's say, a high-risk scenario. Then we are also making some work to integrate these automatic assessments in the European Assembly worksheet that is being used in several industries, EAWS, to give automatically score about the scores that usually the ergonomics ergonomist does by visual observation. So he evaluates the angles that the person is standing, even if he's bent forwards, strongly bent forward. We try to make this evaluation in particular in some way automatically and as a tool to support the ergonomists at their work. And we are actually pursuing in some more depth about some research questions about biomarkers to measure motion efficiency. This is a work that is also being in a transatlantic collaboration with a lab in the MIT, is where we are pursuing some research questions with regard how to measure motion efficiency and how to get biomarkers about our motion to measure this effort efficiency ratio. And we are measuring the smoothness of the movements, the variability, and the overreach, which is when the operator reaches a position which is not supposed to in so far. And the goal is that these overall biomarkers will serve as an evaluation of the experience level of the operator and also at the fatigue. So with these new biomarkers that we are pursuing, we can address also these variables. This is the architecture that we are proposing. So we have sensors that will collect cross-quantitative data like productivity, cognition, and ergonomics. Those sensors will stream data to edge nodes that will aggregate this data. And then this data will be streamlined to a central server, which will deal with the processing of the data aggregation, and then share this data with a dashboard that industrial managers can see and evaluate the KPIs during the working shifts and access this information. This is an example of a dashboard that we are drafting. So you can see that we have access to the productivity rates of groups of operators. We have access to the variables about the self-report that I've been addressing. And then we also have a dedicated user interface to support, to show the results of the ergonomic risk assessments evaluation. And this presentation that have been so far, so we have focused in several domains with regard even to the health and being more proficient or more productive with regards to the operator. So we are reaching now towards the operator of the future, the operator 4, where with this type of technology, such as the wearable, the operator can be plus health. Even we are considering also to extend the research that we are pursuing to another domains. One of them is collaborative robotics, then super strength like exoskeletons, super intelligence to combine this data with the AI, and perceptive with the augmented reality to help the operator in diagnostic tasks and also for operator training. And thank you, and I hope you enjoy the presentation. We're happy to have questions at the end.
Thank you, Eva and Duarte. And now the session is about using blockchain technology to improve the supply chain processes and ease the certification of agri-food products. Eva and Carlos, your turn.
Yeah, I again. So now I'm going to present the project Smart AgriChain. Yeah, so it's a showcase of Smart AgriChain project. So the problem in Smart AgriChain that involves Smart AgriChain project is that many farmers, producers, and vendors face the challenge of defining of defining the best in order to the best solution for securely and reliably define their product management stages in order to identify opportunities for improvement in its operation, as well as to obtain certifications and quality assurance in a quicker way. The challenge here is to define the best solution to safely and reliably interconnect all stages of product management, to identify opportunities for improvement in your operation, as well as obtain certifications and quality guarantees more quickly, eliminating a whole set of bureaucracies and time-consuming processes. So the problem here is that these supply chains involve usually many intermediaries, bureaucracies, and complex operations, and making it difficult to guarantee sustainable management of all the stages through which the product passes until it reaches the final consumer. On one hand, the consumers are becoming more and more demanding about the products they consume, and they want to make sure of the origin and underlying process of the product they are purchasing or consuming. And on the other hand, we have private sector that is more and more eager to introduce technological advances in supply chains to control over all of their stages and be more economically sustainable and increase their competitiveness. So Smart AgriChain will have the objective to carry out the research and development of a web-based solution to support entities related to the production and commercialization of agri-food products on improving their supply chain processes and ease the certification of their products. The platform will make use of blockchain technology to modernize and strengthen the security of supply chains management for producers and vendors and ensure transparent traceability of the products in all phases. So we are expecting to simplify speed and improve the certification process of agri-food products, to support producers and vendors on optimizing their supply chain, to establish a trusted relationship between producers, vendors, and consumers, to democratize access to certification services for small agri-food producers, to promote the value of sustainable and eco-efficient products and processes, and to strengthen the position of Portugal and Europe as providers of agri-food products of excellence. So with our platform, we are going to make sure that the features that we have is trust and transparency, swift asset transfer, smart contracts, faster transaction flow, fraud detection and prevention, traceability and security, and finally, digitalization and visualization. So regarding our end users, the platform will have producers and vendors that can discover certification entities, access updated legislation, requires consulting services, and smoothly obtain certification that is now very hard from licensed entities and offer product storytelling. We are going to have also certification and consulting entities to ensure producers and vendors meet the requirements for certification and offer services and improve monitoring and inspection. We are going to have logistics, distributors, and retail that can access the data on the product's path and submit information on distribution and retail process. And finally, we're going to have end customers that can easily and quickly access authentic information on the history of the products they wish to purchase from the farm to the table. So we are now onboarding two end users, Adega de Favais and Caos Primavera, that are focused on beverages. So regarding the business point of view, I'm gonna introduce you my colleague, Carlos Oliveira, that is the product owner of Green Pact that is the product that Smart AgriChain is behind.
Thanks, Eva. And so I'll just give you a little bit of a view as to how we think of incorporating the results of research and innovation projects into business products like GreenPact, and how Zenithings is planning to apply those to market and bringing those to a wider set of stakeholders that benefit from the technology that we're building here. GreenPact is essentially the corollary of many years of research and investigation at Zenithings, where all of this technology that you guys have just heard about gets rolled up into a platform that allows companies to position themselves as sustainable by virtue of adopting a technological product that's supported by humans that provides a sustainability department as a service. Fabio? So what's the problem that we're trying to address here? And I could ask you to move to the next slide. The problem really that GreenPact is looking to address is that, Fabio, next slide, please. Thank you. As companies try to move towards climate goals and take sustainability concerns as one of their primary targets for the next 10 years of operation, there's a massive challenge at hand, right? Which is, how does a company manager, a company owner, a small business become carbon positive by 2030, right? And whether you're a small business or a large corporation, the reality is that continuing to increase emissions and just offsetting them elsewhere just won't continue to do. And it's really, really hard to understand where to start. So GreenPact comes as a solution for these problems, where we're essentially, next slide, please, positioning ourselves as a sustainable supply chain as a service. What GreenPact does, really, is to allow any company to come on board, digitize their entire supply chain, and quickly understand where and how to make an impact, so that they can move from where they are into becoming climate neutral by 2030 in a progressive manner, without compromising any of their business objectives or without being overwhelmed by the amount of effort and work and investment that it would take to become climate positive by that time. Next slide, please. So there's essentially two sets of stakeholders here, and for manufacturers or for any company that owns their internal operations, what we essentially do is we start by integrating with whatever systems they have in place already, whereas supply chain management tools, ERPs, any digitization activity that they're continuing to pursue, like IoT devices, employee tools that they have in place. We create a blockchain-based evidence record based on the technology that's being developed under Smart AgriChain. We use machine learning to identify measurable improvements in production. We map out the entire supply chain and represent it virtually in our platform with a digital twin. And then from that initial set of data, we lower the cost of compliance, the cost of quality control, the cost of certification, and give companies a single sustainability ratings that their customers understand. Essentially, this single sustainability rating is how we help companies position their improvements as they make progress towards becoming more sustainable. We created a framework that looks at community, labor, environment, animal welfare, to understand how brands and manufacturers behave in each of these dimensions, and to help them communicate to partners, to suppliers, to consumers, how they're positioned and how they're doing and how they're progressing in each of these dimensions, so that their sustainability efforts get valued by the market, so that they clearly can communicate to consumers what the value in each of these changes are, and so that they can extract some of the business value in becoming more sustainable as they go, and position themselves as sustainable brands and greener brands with actual effort put into making their entire operation more sustainable. For brands and for anyone starting a new business, we essentially take anyone that's already on top of the platform, we vet them, we, based on this GreenPact rating, this framework that we've created, give them a full-fledged production platform where they can design and source every aspect of that product, track the production process every step of the way, test their batches and scale as they grow according to both the business and sustainability criteria, and then help them distribute them across their direct-to-consumer or e-commerce channels. Which essentially takes us to what the ultimate benefits for all of the end users of the platform are, whether it's brands and suppliers that we're focusing on, where they can essentially bring certifiably sustainable products to market. Eva was mentioning the work that we were doing in the food and beverage industry, where the blockchain evidence records, the machine learning aspects of the platform, and the fact that we're digitizing a lot of the supply chain processes allows them to then interact with certifiers in the market to create the sense of validity around the actions that they're taking to make their product much more sustainable. We give them access to specialized supply chains with partners that have already been vetted and rated within the GreenPact framework. And we give them analytical capabilities so that they benchmark themselves against the market and figure out where improvements may lie. Then for distributors, for people who are selling these products, we're able to aggregate valuable meta information about how sustainable they are and in which dimensions, so that, for instance, as consumers purchase them online, they can filter for these attributes and identify products that are more akin to their values. And we allow them to cater to new customer segments in these sustainable markets that are growing much faster than regular customer segments that they wouldn't be able to cater otherwise. And then for end customers, for all of us that are purchasing products and are looking to adopt more sustainable consumer patterns, we allow you to make informed decisions and to personalize your shopping behavior, again, according to not just what the economic outcomes are, but also to the sustainability aspects of each of these products. That's us. Fabio, we get back to you.
Thank you so much, Eva and Carlos. Now, there are any questions? I really think not. So I think that's not the questions to make. Thank you so much to all the viewers. We hope you enjoy it. It was an honor participating in the European Big Data Value Forum 2021 with our two projects. Thank you so much. If you have any questions or information requests, we can contact us. Thank you. Stay safe and see you soon. Goodbye.
Goodbye. Thank you.
Okay, so hello everybody. I'm here to present a national space data initiative, and I'm very happy to have this opportunity. My name is Ann-Kristin Eriksson. I work at RISE since a couple of years, and I work as research program manager, amongst other things, with this National Space Data Lab initiative. It concerns Earth observation data, and my background is in this geographical information system since before RISE, and I also have a medtech and telecom background. And my plan for today looks like this. I will start to say some introductory about why we are doing this, what are we doing, why now, what are the enablers, and in the end I will summarize what we mean by this National Space Data Lab of Sweden that we are doing together with our partners. So let's go. So the needs. We all know that a lot of things are happening with the globe, and there are increasing needs for keeping track of environmental changes. And this can be done by Earth observation data and with the satellite missions up there. And the use cases are very wide, but it could be about climate adaptation, it could be about forestry, about growth, water levels, and so on. And we all know also that we have this Agenda 2030 about sustainability in the world. So lots of use of the Earth observation data. And to be able to use the data, we need innovation hubs, and we need efficient innovation hubs. So therefore, our mission in this surrounding is to make the world more sustainable, and doing this by implementing a knowledge and data hub for our observation data, and then apply AI and other methods to this big data, and look at the trends, look at changes in the environment, and give decision makers support for their decisions. So that is our mission. And we also see we have this European strategy for data, and it will be implemented in national strategies for data. And this is right on spot as well for this mission. So why now? And what are the enablers as it looks now? Well, for the first, the space industry is growing tremendously, and the data is exploding. This is a little bit of old picture. It ends 2015, but it gives the idea how the data is exploding, the available data from satellite missions out there. And if we just look at the European Space Agency, we in this initiative, we are mainly focusing on Copernicus program, and I will tell you a little bit more about that. But that is not the only program only for ESA. You have the science missions and you have the weather related missions as well. But for us, we have started to use the Copernicus data. And this is the next enabler. It's the world's largest program for daily collection of space data. And maybe the most important thing is that it's a long-term commitment from the European Space Agency, and it's full, free, and open access to data, the idea here. And as it is long-term, stakeholders then can have the courage to invest in this for a long term. on forward. In our initiative here in Sweden, we have been so far, since the start, 2019, we started with this initiative, we have been looking at the Sentinel-1, 2, and 3. And the Copernicus program continues to deliver. So we have Sentinel-5 pollution, for example, and so on. And again, just a summary, this is from the Copernicus messages that it's climate change, it's marine, it's land monitoring, and it's also emergency management as examples. So the use cases are very wide. As this is very, very big data, you need compute power and capability to handle all these data. So what is included then in our initiative is that we tailor the data for Sweden and the region up here in the north of Sweden, North Scandinavia, the Baltic Sea. We have a data center at RISE in Luleå, in the northern of Sweden, very close to Esrange and other kind of the space industry stakeholders in Sweden. And the data center we use now is a very energy effective data center. And just to say, that's a lot of data centers in the area. For example, we are just a couple of kilometers from the Facebook data center site in Europe. And the reason for choosing this area for the data centers is, for example, that the river close by, the Luleå River, is giving 15% around that of all the production of energy in the whole country. So we are in a good place. Also, when you have this compute power, you need concepts to structure the data and to ensure the quality. And I'll give you some examples now of some of these concepts that we have used so far. First of all, the concept from Australia called Open Data Cube. It's developed by the Australian geoscience community, and it's used in the Australian Data Cube, or what we call now the Space Data Lab. It has been used by Swiss Data Cube and their initiative in their country, also Digital of Africa, Brazil, and now we are using it. And a short kind of popular description of what is Open Data Cube. You can see that as you have a map, and then you add time, giving you this cube. Or you have this map, you have frequency bands, like in Sentinel-2. You add different frequency bands. What is the value here? Well, it helps you organize the data, and doing it from various satellites, it gives you the opportunity to use Python, which is a very popular library. And you can easily make time series analysis on this big data of Earth observation. And you can also connect it to some of the key software, commercial software already out there, and integrate it. What we're looking at right now this autumn is Open Earth Observation, a quite new concept. And it's also defining an interface between the infrastructure, the platform, and front-end applications. So these we are implementing as we speak. And also there is a concept called Stack. And the Stack concept also makes the assets searchable and make it easier to use the data. And as I said from the beginning, you need methods to analyze the data. And at RISE, we have a lot of AI capacity. This is the RISE network picture I stole from them, just showing all the areas that RISE is included. And RISE, I hope I said that from the beginning, but it's the Research Institute of Sweden. And we are in a lot of areas and wide areas. So these round circles here about built environment, climate change, and so on, is that what we see is related to this National Space Data Lab initiative. And then you need partners. You need to cooperate. It's complex. We live in a complex world and we need to cooperate. And we have done cooperation by having a tight dialogue with the use case owners. And we have developing this platform for Earth observation, what we call now Space Data Lab, together with a lot of use case owners. So we have been running, I think it's 10 pilot cases, proof of concept cases up until now. And this is a picture, just a summary of some of the partners. Up in the left corner, you have the 4 partners from the beginning. So we also have AI Sweden as a strong AI competence organization. We have the National Space Agency here, and also the Space University in Sweden, Luleå University of Technology. So these are the 4 initiative stakeholders driving the first project from 2019. And then we have all these use case owners, and this is just a picture of Swedish authorities working with forest or with properties or with agriculture and things like that. So it's about 15 in this community that needs Copernicus data. It's called the Copernicus Corporation in Sweden. And then we have the enablers that I talked about, and also, of course, we need funding for this. And Vinnova has been a very important part funding this. We are also part of the EU project where RISE is the only Swedish partner that is called European Hub for Data, the Federation of Data-Driven Innovation Hubs. And here we offer space data to the SMEs that could search for funding for experiments. I just listened to a new appointed professor at the Space University here in Luleå. So I stole this picture where he kind of presented connecting topics, a network of partners from the Luleå University perspective. So I just wanted to show you that. I mean, we have S-Range, there's space corporation companies, and they invest a lot, Luleå Technical University, to have programs in this area. And we are here. The RISE site I work at is here in the north of Sweden. See, and this is also a picture for where we have these orbital launch sites. So it feels good to be very close to the S-Range site. Okay, so I'll try to summarize what are we doing then? We could call it Digital Earth of Sweden, or Digital Earth of Northern Scandinavia, Baltic Sea, or Space Data Lab as the name is now. But to summarize, we use the Copernicus data. We have strong compute power and storage. We use these concepts. We add AI, and in the future also other data sets for data fusion to give the decision makers decision support, for example, in the climate adaptation area. I forgot to say that I was supposed to say that you should put your questions in stage 1 chat, and then I will have it in the Zoom chat. And I will save a couple of minutes in the end for your questions. So please put it in the stage 1 chat of the event web. again, a summary to make the world more sustainable. We think that the Space Data Lab, in connection with all other European and global space data labs, is something very, very valuable here. And last but not least, there has been a governmental assignment just a couple of weeks ago, where the government has said to the Space Agency, okay, look at what could be done very long term in this area. So that is ongoing now for this Space Data Lab. And it's again the reasons that the government of Sweden see is this sustainability goals and also the European data strategy goal. There is a landing page. It's under development, but it's already there. It's spacedatalab.se. Here you can find information about the ecosystem, the partners. You can find short information about all the pilot projects that has been going on up until now. And take a look if you're curious about this. So a couple of minutes left for questions. Sorry for forgetting to mention the stage 1 part in the beginning. So you can also, if you'd like, you can just shout out if you have any questions or comments, or you can contact me afterwards in the event structure, or you have my contact information and email on this page. So please reach out if you're interested. And thanks for having me here at this final event. So yeah, I'm reading a chat here. So let's see, I can kind of conclude. The conclusion is that we are going to continue this journey. We now have the governmental request to look overall from a national perspective. And I think the Space Agency of Sweden are going to give their report in March next year. And I can also add that we are cooperating a bit, or have started a cooperation with the Finnish Data Lab, because we want to have the Baltic Sea a part of this data tailored for this region. So that cooperation has started as well. I didn't have that on the screen. But it's so much fun to work with this. We are a team of people here at RISE together with the people of the other partners, and it's very interesting, and the users are very keen on having everything ready yesterday. So it's great to work with this. Okay. Okay, so thanks. That was my conclusion. Thanks again for having me here.
Hi, thank you for joining this session organized by Infor, a European project that stands for Interactive Extreme Scale Analytics and Forecasting. My name is Antonis Deligiannakis. I'm the coordinator of the Infor project, and I'm going to give a short overview about the challenges and objectives of Infor. So Infor is a research and innovation action that started about 3 years ago in January of 2019 and finished about 4 months. Athena Research Center is the coordinator, and I'm physically coordinating this action. The budget is about 4.4 million euros. This is a consortium of Infor, consists of the Athena Research Center, National Center for Scientific Research Demokritos, RapidMiner GmbH, Barcelona Supercomputing Center, Spring Techno GmbH & Co., Marine Traffic, NATO Science and Technology Organization, NATO STO CMRE, Istituto Italiano di Tecnologia, and Fundatio Centre de Regulatio Genomica. Now, let me give a brief introduction about the problems that are addressed by Infor. So data analysts are often not expert programmers, so it's very hard for data analysts to code, program, and then debug complex data analytics tasks. And when writing the code, it often takes many hours for the code to run just to figure out that something has gone wrong. Also, it's very hard for the data analysts to optimize their code. For example, if they have some operators that can be executed over multiple available big data platforms, which ones to choose for each operator? Moreover, there are many applications that are really good at simply detecting events of interest, but it's much more useful to forecast future events of interest. For example, in the life sciences applications, it's very important to forecast the emergence of resistant cells by detecting small changes in physiological or molecular markers. At the financial sector, it's very important to forecast price swings or to detect investment opportunities. At the maritime domain, it's very important to forecast and proactively respond to some dangerous events that happen at sea, such as vessel collisions, piracy, or vessel groundings. So the question is, can we forecast the outcome of a time-consuming operation before needed to complete this operation? So the main objectives of Infor are, first of all, to develop an open source tool to graphically design data processing workflows and complex data analytic tasks. Using this tool, the data analysts will need no programming no code to write, and the optimizer will take care of any decisions that needs to be taken care of, such as which operator will be executed in which big data platform and how the jobs at these big data platforms will start executing. Also, we develop real-time interactive machine learning and data mining tools, and to enable scalability, we make heavy use of data synopsis. Also, we have tools for efficient and accurate distributed complex event forecasting. We have 3 use cases at Infor. The life sciences use case studies the effect of drug synergies in battling cancer. And here we have a huge number of simulations that take place, but most of them are non-promising, so the patient dies. So we need to quickly detect the most promising ones and to be able to forecast which simulations may lead to some promising scenarios and kill the rest of them. So for the financial use case, we need to be able to forecast investment opportunities, to detect whenever there is systemic risk at the stock market, or to be able to forecast price swings. At the maritime domain, we need to be able to detect complex events that happen at sea by fusing data by many sources, such as satellite data, data from unmanned vessels, data from stations at the surface, or even underwater sensors obtaining sonar data. So this is a brief introduction by me. Thank you. Please make sure to follow us at the social media. And the next speaker is Fabian Tem from RapidMiner, who will speak about the architecture of the Infor project.
Thank you, Antonis, for the introduction. So my name is Fabian Temmer. I'm a data scientist at RapidMiner, and I will give you now a short introduction into the architecture of Infor with the goal to make streaming data processing easy for everyone. So let me just start with just recapping what Antonis just said, the main objectives of the Infor project regarding the architecture. So the top is what we were aimed to do. We want to build a holistic, pluggable, extensible framework for extreme scale streaming analytics. And the main objectives we focused on was we want to provide a possibility to have graphical workflow design for non-programmers, as Antonio said, so that users can actually design their streaming data analytics in a graphical way. We want to have an optimized and automatic execution of these workflows on the underlying big data platforms. And we want to integrate advanced analytics functionality like data synopsis and complex event forecasting so that the user of the Infora architecture can simply use them in their analytics. And I just want to show now the main high-level concept we developed for the architecture to achieve these goals. So we have a few different components we designed, and one of the main important components is the graphical editor component. Obviously, if we want to provide the functionality to design graphical workflows, we need to have a component which is able to do this so that the user can actually see this. And we will see this in a few moments in more details how this is achieved in the Infora architecture, but this is one of the main components. Next, we have the manager component, which takes this graphical workflow and actually deploys on the computing clusters on the supported big data platforms, in our case, Flink and Spark platforms. As Antonio has already said, also one of the main objectives is to automatically optimize this graphical workflow. So we have an optimizer component, which is interacting with the manager component to receive the workflow designed by the user and optimize it to have an optimized deployment plan for the workflow on the computing clusters, depending on the available resources and other conditions. And finally, we wanted to introduce and integrate so-called, we call it the advanced analytics components, could be online machine learning, Synopsys data engines, complex event forecasting, maritime event detection for some support of use case and specific things. And of course, these components on the one hand has to be developed and they are integrated in the Infora architecture that the user can just use them like any other normal, more simple operations in the graphical workflow by just dragging and dropping them into their workflow and utilizing the functionality in their specific analysis goal. We will later see some more details about the complex event forecasting functionality and also the maritime event detection, and also some details about the optimizer components directly after my talk by Nikos Georgakos. So I will focus on the top part of this concept from the graphical editor through the managed component, how it's then actually deployed on the computing cluster. And therefore, I want to show you actually a live demo of the Infora architecture in working. So this is RapidMiner Studio. This is normally a program to actually design batch processing data science processes in a graphical way by dragging and dropping operators in this panel in the middle. And in the Infora project, we enhanced it with the so-called streaming extension, which allows us to design also streaming processing workflows in the same manner, and which fulfills the concept of the graphical editor component in our Infora architecture. First step, what we have to do is we want to connect to some big data platforms, so we actually have to define these connections. So what we can start, we have here this repository, and we add here new connection objects, and you see this is still like by clicking, you say we have few connections supported. In our case, we added the Flink cluster connection. We give it a name like EBDF demo, and then you can enter the connection information you need to have to be able to connect to the big data platform in this graphical user interface. And then you can store it in the repositories. You have to do this once, and then you can utilize it in any process you want to use. And you see here, I have already created some connections to a Flink cluster and a Kafka cluster, which is running on a research server, which is called Freya. That's the naming. So this is already, so can you already use it. So to showcase this demo, I want to show the different steps. So the first step is we have prepared a demo data set in this Kafka cluster. And first step in this analysis is normally just to look into the data. Therefore, we implemented operators which called read Kafka topic, for example. So I just dragged and dropped in the operator and the Kafka connection. I connected here, and I just type in here which Kafka topic I want to use. So this is now retrieving from the Kafka topic input. I can configure some settings here, all in a graphical way. And this is just reading in, and then I can process it in a batch way. So I can, in this case, first investigate it. So I'm just running it, and it's retrieving the data from the input topic and providing it me in the result view of RapidMiner Studio. And there's some more parameters here, but the most important part, these are different messages one by one. In this case, it's only batch processing, but want to do some investigation. So this is some ship position data. We have a timestamp here. We have an identifier, and also we have a longitude and latitude here. So it just investigated this. And now I'm going back to my process panel. Next step, after I have looked into this, I want to have an analysis of this and a and streaming processing analysis, and therefore I actually now use the graphical editor to design this process. So, so what I have to do is I insert first the Flink cluster on which I want to run this streaming processing workflow, and then I'm using the streaming nest operator where I will design my workflow in it. And I connect it here, and this is all I need to do to actually deploy it later on the Flink cluster. I give it a name. And then I can go inside the streaming nest operator by just double-clicking on it and designing the actual process inside it. Again, I will start with my Kafka cluster because it's my input data, and I want to use Kafka source operator, which is my input data, and later I want to also push my output data also in the Kafka cluster, so I'm using a Kafka sync later. For all of this, I'm connecting this Kafka cluster here to both operators, so I'm using the same Kafka cluster, but later with different input topics, with different topic names. So I start with the Kafka source, and my simple demo process, I think about maybe the situation. I have my routine position data. I want to maybe have a simple filter to the position data. So maybe I want to filter for ships which crossing a specific threshold in the latitude coordinates. So I'm just using a filter stream operator here, which I'm connecting to the Kafka source, and the key was called latitude, and I'm just copy and pasting the threshold coordinates here. So I'm configuring here, and when they are crossing this line, I want to create a warning message. So I'm adding a map stream, which I'm calling here message, and I'm also copying the actual message I want to add there. So in this case, it's just a warning, ship enters critical zone. This is just a simple example for the demo purpose. And then finally, I want to push this output data to the output EBDVF topic. And now I just click on the run button. So I've designed the streaming process, click on the run button, and it's now deploying on the Flink cluster. And while doing this, I go back to my presentation to actually show you how this is internally working. So what you see here, the concept of the manage component, and on the top level, you see the actual RapidMiner Studio with the operators. And you may have seen no of the operators are actually technology dependent. There's nothing of Flink or Spark in it. It's all the logical functionality. So this is the only thing which the user has to worry about, how this is the analytic logic is built up. The manager component convert this into a framework independent graph, so RapidMiner independently, and then convert it depending on the connection I provided to a Spark or Flink specific one, so that can actually be deployed there. So going back to my process, it's now deployed here. We can monitor it. We see it's running, and I can finally, so we have it now running on the Flink cluster, and I can finally go to my third process, which is also using, again, the read Kafka topic operator now for the output, and then do some post-processing that's just dragging and dropping in so that we can investigate a bit more, a bit easier. And now in the output topic, we have the messages now a bit more easy distributed. And you see here, the message was entered for the events which were crossing the latitude the latitude position. So let me just go back to the presentation. So again, the overview over the Infora architecture. I hope I could show you how we can utilize the top graphical editor, the manager component, to design workflows in a graphical way and actually deploy them on computing cluster. And just want to really shortly show you how you integrate the advanced analytics components. We could go back. So in this example, we had the streaming analysis process, and we used a simple filter to do the actual analytics. This is obviously relatively simple, but we could also, for example, just use the complex event forecasting component instead of the filter. No, should not delete this one. Instead of the filter, just connect it here, connect the output. I need a complex event forecast, the Kafka cluster also for the communication, and the Flink cluster where it should be deployed. Well, I've already set this up. And then I have to have a bit more complex, more advanced parameterization of this. But now I could utilize the complex event forecasting to actually do the filtering instead of the simple filter, and can utilize this functionality in my process and could deploy this process. So this is the Infora architecture in a nutshell. In a few minutes, as I said, we see a bit more details later about the complex event forecasting and the maritime event detection. And now Nikos Giatrakos will talk about the optimizer component. Thank you.
Thank you, Fabian. So, hello, everyone. I'm Nikos Giatrakos from Athena Research Center, and we are going to continue by talking about cross-platform optimization of data processing workflows in Infor, workflows such as those that were designed by Fabian in the previous presentation. So, again, to give a bit of the context here, we are operating over network architecture, which are composed of a number of clusters and data production devices. In this example, we have a black, a green, and a red cluster for exhibition purposes, and each of these clusters can run one or more big data platforms such as Apache Spark, Flink, or Kafka. Our aim is to execute workflows globally on top of this architecture, making appropriate use of resources so that our analytics keep running in a real-time fashion. So we have analytics workflows that are running continuously, and we want them to provide real-time answers to the applications that have deployed these workflows. And in order to do that, the first thing we should do is to use RapidMiner Studio and include connection components to the various clusters and big data platforms that we have available. This is what you see over here on my mouse pointer. The second thing we should do is to use a streaming optimization operator, which is provided by RapidMiner Studio, which essentially instructs the Infor architecture that the workflow we are about to design should get optimized. And in order to execute the optimization process, we provide a suite of optimization algorithms to which we are going to refer shortly. So after that, we should double click in this operator, in this streaming optimization operator, and design our workflow. What we actually design is a logical workflow. So it incorporates the application logic, but it is deprived of any physical details on the actual execution that will take place. The role of the optimization process is to come up with a physical workflow, that's what you see on the right of the screen, where for each operator, we prescribe the big data platform, the cluster, the big data platform, and the parallelism that it should be executed with. But we have different options, of course, and we should be able to judge which physical workflow is better than the other. In order to do that, we incorporate a number of performance dimensions, such as throughput, the number of tuples being processed per time unit, network and processing latency, communication cost, and so on and so forth. We can incorporate any performance dimension that is of the essence. If we do that, in this example here for a three-dimensional space, each physical workflow corresponds to a dot. And what we want to do in our optimization process is to distinguish the red dots from the blue ones. This is because the red dots are actually physical workflows that are not dominated in every performance dimension by others. And after we have that, after we have these Pareto optimal plans, as they are called, we want to deploy the physical workflow that provides the overall lowest cost, and the cost is actually computed as a weighted combination of the various performance dimensions. Furthermore, here we may have constraints to specific dimensions such as latency constraint or communication constraints. So the generic view of the optimization process looks like this. First of all, we should have some cost models in order to judge how good a placement of an operator in a cluster and big data platform is. Because we want to be able to accommodate any given operator, we do not assume we have an analytic formula that describes the performance of each operator in various clusters and big data platforms, but instead we develop a machine learning based cost model. We execute a few a priori benchmarks in order to see the execution performance of each operator under various clusters, big data platforms, and parallelization degrees. And we use the statistics that we collect from there in order to train machine learning based cost estimation models. If we have this cost model here, then the logical workflow is given to the optimizer in the form of a JSON file, and the optimization process continues by creating a number of what-if scenarios. So we start from the bottom of the workflow that I was showing in the previous slide, and we go, which we call the upstream operators, and we go to downstream operators to the end of the workflow. So for instance, the optimizer asks, what if I place this upstream operator in the black cluster using Spark? And of course, prescribing different parallelization degrees, which are omitted for exhibition purposes, for ease in the exhibition. Or what if I place this operator in the red cluster using Flink? And having done that, for every upstream operator, we proceed downstream to the workflow. Having placed the upstream operator in the black cluster using Spark, what if I place the downstream operator in the same cluster? Or what if I choose the green cluster running Flink for the downstream operator? And so on and so forth. And at each step, we aggregate performance predictions that are provided by the cost models. We have an overall cost for every possible physical workflow, and we pick the best one in order to prescribe for execution. Now, while doing so, we provide, as I said at the beginning, we have different options of optimization algorithms. Our optimization algorithms differ in the number of what-if scenarios they provide. So they trade their own execution time for the goodness, how much near to optimal is the physical plan they prescribe. And we have exhaustive search algorithms which examine every possible what-if scenario for the entire workflow. We have heuristic algorithms which for each upstream operator keeps only the what-if scenarios that are locally Pareto optimal, so up to that point of the workflow that we have examined so far. And we also have greedy solutions which keep only the best what-if scenario, the scenario with the best overall cost up to that point of the workflow we have examined so far. So having determined a physical workflow, we actually deployed it in the various clusters and big data platforms that we have available. But even if we do so, we are not done yet. What we should do next is to monitor the execution performance of the workflow so as to first collect statistics, because we need them. Using these statistics, we update our cost models incrementally. We do not need to train in anything from scratch. We avoided the cold start at the beginning, and now we have live statistics to improve our cost models. And furthermore, we monitor the execution, because if we see that the performance of the physical workflow deviates a lot from what we predicted, we perform runtime adaptation, coming up with new physical plans. In this particular example, for instance, we may have a new physical plan which switches the position of these two operators at the top of the slide. And in order to accomplish all this, the optimizer has its own architecture. We have at the bottom, we have, of course, the various clusters and big data platforms. We collect statistics via JMX and Slurm. We ingest the statistics in an ELEC stack. Statistics are used by the benchmarking component, as I said, in order to avoid the cold start. They are fed at runtime in the cost estimator, and then whichever optimization algorithm we choose interrogates the cost estimator to derive performance predictions. What we have finally achieved is to develop the first optimizer for cross-platform network streaming settings which can incorporate any given operator, either it is data mining, machine learning, pattern matching, or stream transformation operators that are provided by big data platforms. We provide the suite of algorithms that may be suitable for different application needs because they trade the amount of time they take themselves to execute with the goodness of solutions they provide. Our solution, optimization solutions, is tailored for streaming settings because we can provide good plans with sub-second latency. We can update our cost models incrementally, not from scratch, and we support runtime adaptation in our optimization process. And furthermore, what we do is generic enough to accommodate new optimization criteria and constraints and to be applied to any new operator that the user or UDF, user-defined function, that may be of the essence to various applications. And with that, I would like to thank you. And Elias Alevizos will follow describing the complex.
I think Miguel will take over now for the next talk.
Okay, Miguel Ponce de Leon will go on talking about tumor simulations in Infor.
Okay, can you hear me?
Yes.
Okay, good afternoon, everybody. My name is Miguel Ponce de Leon. I'm researcher at the Barcelona Computing Center, and I will be presenting the life science use case, which is in online exploration of multi-scale simulation of cancer growth. So just as a brief introduction, cancer is a group of diseases involving abnormal cell growth with the potential to invade or spread to other parts of the body. And a big challenge in treatment development is avoiding the emergence of resistant cells. So complex multi-scale models of tumor growth can allow us to run in silico experiment. And those this kind of simulation can be used to understand the mechanism behind the emergence of cell resistance and those resign more resilient treatments. So multi-scale laser-based simulations allow the integration of different modeling approaches, and they can be seen as a virtual laboratory. So the idea is that we can customize these simulations to mimic a particular patient using molecular data and then run in silico experiments like a virtual human to decide which is a better treatment in order to avoid the development of cancer or the progression. So on the right side, you can see a brief overview of what this multi-scale model look like. So we have an agent-based model in which different agents represent cells, and inside the cells we have different molecular models that describe the behavior of the cell and how the cells respond to different treatments. And these cells are growing and developing in a microenvironment, and this microenvironment is used to simulate the diffusion of different molecules, such drugs. So in this simulation, we have different algorithms for simulate the different components, and those we have also different time scales in which the different processes take place. So we have developed a prototype model of a tumor growth in which we can provide a particular drug that binds to a receptor of the cell and may trigger the death of that cell. But if the cell is exposed for a long, they will develop resistance, and then they will not die because of the treatment, and they will keep growing. So the model has several components you can see, but on the context of this presentation, what it's important is that those simulations are computational demanding, so they take a lot of time to run these simulations in a computer, and they produce complex big data output, which include the positions of the cells, the state, and the state of the microenvironment at different times during the simulations. So in our use case, we want to use this simulation to optimize drug scaling, so the way or the timing in which drugs are administered into the tumor experiment. So we have the different steps. The first is the model definition, so where we define what is our model, what are the parameters, and so on and so forth. Then we have a calibration step in which we use experimental data to find and tweak parameters of our model. And finally, we use our model for model exploration, which is, for instance, find the optimal treatments using optimization techniques. So this is our workflow, which is based on EMUSE, which is a framework for extreme model exploration with Swift. And the idea is that we have a workflow which could be a genetic algorithm, a sweep, a covariance metric adaptation, any black box or derivative-free optimization technique. And also the workflows basically ask the model exploration to generate parameters. The parameters are plugged in different simulations. Simulations are run in parallel or concurrently. After the simulation finish, we gather the results, we learn from the result, and we generate parameters. So the problem here is that the parameter space are huge, even with few parameters. The evaluation of candidate parameters is computationally expensive, and most of candidate parameters are informative, so are not useful. So the solution we have found in the context of INFORE project is performing online exploration of the simulation trajectories and early discarding an informative parameter set. So speeding up the process of parameter exploration. So this is the architecture we have extended from our previous workflow. This is the online version. So now we have an online producer, which is listening the stream of the different simulations that are running in parallel, and it communicates to a complex event recognition model, which will tell or forecast if a particular trajectory is not being informative, and then it will tell the consumer that this simulation should be stopped and a new simulation should be run, so that the action is performed. So this is more or less the same, but with more details. So we got the Muse that it's evaluating several parameters. Those parameters are running the Mare Nostrum supercomputer, and each simulation is streaming the data into a Kafka server, which is connected to RapidMiner. And in RapidMiner, we have implemented this complex event recognition, which is different, listening to different topics and deciding whether the simulation should be killed or it should be let run until the end. So these are just preliminary results. This is, sorry for the typo, this is a standard model exploration. So we run around 3,000 simulations, and it takes like 10 hours world time. We don't discard any simulation here. And most of the parameters here are non-informative. So in the green curve, you can see the exponential growth of cancer cells. On the contrary, when we perform the online exploration plus the early killing, we are able, we run the same number of simulations with same parameter, but we are able to discard 90% of the simulation early before they finish. So we use a third of the total computing time. So by running this online exploration and the early killing of simulation, we are able to save around 67% of the total computing time that it would take if you use the standard model exploration approach. And it also reduces the computing resources usage. So in summary, multiscale simulation can be used to in silico investigate treatment strategies in model of cancer. Models have complex parameter spaces, which we can run in 1,000 computational demanding simulations. But online analysis of simulation trajectory can accelerate the model exploration. And this acceleration is a critical step in the roadmap to scale up simulations in size and in complexity in the road to virtual humans. So on the right side, you can see just a roadmap for future complex and bigger simulations. So that will be it. Thank you for your time. And I will introduce Holger Arndt from Spring. He will be introducing the finance use case. So thank you very much.
Oh, yeah. Hello, my name is Holger Arndt. I will present the INFORE financial use case. I'm managing director at Spring Techno, a company, an SME based in Germany, and we focus on big data and artificial intelligence for professional traders in the financial markets. So there is the INFORE financial use case, and we do big data for performance. The data in the financial industry is very rapidly growing. There are about 1.5 billion new messages added every day, and the yearly growth rate is estimated at not less than 30 to 50%. We focus on hedge funds and their needs, also banks and private traders. And in the hedge fund industry, the needs are very clear. It is the so-called alpha, which says that the hedge fund wants an overperformance over the benchmark, which mostly is the S&P 500. Then our clients want portfolio optimization. They have mostly ready-made portfolios or some portfolios they and markets they invest in, and they want to optimize inside these markets. A big point is risk management and risk mitigation. We have systemic risk as a big factor, and also hedging against downturns. And the Infor application in the financial use case provides hedge funds with all these tools. What we do is to explore multi-layer financial dependencies to reduce systemic risk. And there is a good quote from the movie The Big Short. Let me put it this way: I'm standing in front of a burning house and I'm offering you fire insurance on it. That's what we want to do. And even we want to start earlier when the house is not already burning, but we warn the financial players of impending risk and systemic risk. The KPIs we have for forecasting price swings and systemic risk prediction are from once to several times per day. So because of the big data load, at the moment, it's for most of our clients only possible to do the full run through the portfolio and all market players once a day, and we want to do it several times a day. And for big data and filtering, our goal, our KPI is 50% faster filtering through the Infor engine. We implement then the benefits of Infor to our existing portfolio of products, which is MaranTrader, ZisRisk Pro, and VectorBull as examples. And let me show you a video that gives an impression of the Infor pilot. So the Synopsys data engine allows us to compute effectively correlations for large amounts of stocks and find the most correlated. Here you see visualizations of nodes for stocks and edges for dependencies. And the nodes are interactive and can be dragged and dropped by the user. Numerical details can be displayed in a sortable table. And to filter the edges, a range slider is implemented. Here you have a second visualization, which we call the carousel, which also gives intuitive view on larger sets on dependencies. The interactive visualization is highlighted on mouse over. And you also can find the range slider to filter the edges. And in addition, you can select a single stock to focus on and see the edges for this stock. So this gives overall a very intuitive overview on correlations that you have there. Yeah, here you can see on mouse over the user exploring different stocks. And these are several other visualizations you can combine on more complex sheets, which allow to perform more complex stock and market risk analysis. For example, you can check the historical dependencies and even forecast future dependencies. So this is an edge we have to go into the future with the exploration of dependencies. Yeah, you can analyze investment strategies based on risk mitigation and backtest and optimize the performance by minimizing risk and check this against a simple buy and hold strategy, where you just buy a stock or a portfolio and hold it through all market phases. The blue line you can see here represents a strategy to sell stocks on higher risk, which results in a better performance. Here you have another visualization for a very important feature of the Infor Financial use case, which is forecasting market prices in stock with a self-learning forecasting algorithm. And the blue lines stand for rising prices and the red lines for falling prices. And whenever the price crosses a prediction line, the prediction was successful. So this can be used by high-frequency traders just to get an overview and to trade against these predictions. So that's all for the financial use case. Thank you. And we continue with the presentation of Konstantina Beretta with the maritime use case.
Hello and welcome. I'm Konstantina Beretta and I'm a researcher at Marine Traffic. I will start describing the maritime use case of Infor. And the second part will be presented by Gabriele Ferre from CMRE. So the title of my presentation is Data-Driven Maritime Event Detection Forecasting over Big Maritime Data. So this is the outline of my presentation. Basically, I will start with motivation and with describing the problem, and then I will explain how Infor helps us address our challenges. And I will just give some more insights about how some of our core components work. Marine Traffic leads this use case. Marine Traffic is the world's leading platform for offering vessel tracking services and actionable maritime intelligence based on the Automatic Identification System, AIS. And another major contributor is NATO CMRE. CMRE is the research center of NATO that conducts state-of-the-art scientific research and development activities and delivers innovative and tested solutions for maritime security and defense applications. And Gabriele will give more details about their work later. So this is a typical day at Marine Traffic. We have to process approximately 70 gigabytes of streams of data that needs to be processed to serve about 1 million users, and we heavily rely on the automatic identification system. The AIS is a collaborative self-reporting system that allows marine vessels to broadcast their information to nearby vessels and ground-based stations. It is based on VHF communication, and although it was first developed in order to avoid collisions between vessels, it proved to be a very valuable source of information in order to increase maritime situational awareness. However, not every vessel carries an AIS transponder, and some of the vessels that do might not use it. For example, this is one of the most searched vessels on the marine traffic website. Its name is Advendaria 1. It was first sized in Gibraltar because it was thought that it would deliver oil to Syria. So right when it was released and it began its journey in the Mediterranean, it switched off its transponder when it reached off the coast of Syria. However, it was spotted by one of our customers, Anchor Trackers, using satellite imagery, Sentinel-1, Sentinel-2, and Planet Labs satellite images. So the problem that we need to tackle is to increase maritime situational awareness by combining global views of data, like AIS and satellite images, with local views of data, like data from thermal cameras and acoustic data. The challenges that we have in this respect is first, of course, the large amounts of data that we need to process, the streaming fashion of vessel tracking data that come in high data rates, the data fusion of heterogeneous sources of data, so data come in different formats and different specifications. And we, of course, need to curate the data, we need to clean the data. And last but not least, we need to derive actionable intelligence out of maritime data. So how we address these challenges and more. The aim is to develop complex event detection and forecasting techniques, to be able to develop techniques for multi-sensor fusion, to use data synopsis in order to address the scalability problems of large streaming data, to be able to design easily interactive data science workflows. We do so by using RapidMiner UI that Fabian showed earlier. And we do all of the above in order to produce actionable information to increase the value of the input data. So the data sets that we process are AIS data, both real-time and historical, Copernicus satellite images, acoustic data, and data from thermal cameras. So provide these data sets as input to our workflows. Where necessary, we apply object detection techniques, more specifically vessel detection techniques, and we derive vessel positions from all these different sources of data. Then these positions are fused in our fusion engine, and individual positions are assigned to vessel trajectories. These trajectories then are fed to the Synopsys data engine in order to create synopses like simplified trajectories with fewer positions per trajectory in order to be processed more easily in the next steps of the processing chain. Then once we have simplified tracks, we are able to derive simple events that can be combined and can produce complex events. Now let's dive into some individual components. How we detect vessels in satellite imagery. We have combined AIS data automatically with satellite images, Sentinel-1 and Sentinel-2, and we have trained a model that is able to detect vessels in images, and then we are able to detect vessels when fresh images arrive. How we perform data fusion. So once we have the detected vessels, we have a distributed framework that is able to assign individual positions to known vessel tracks in order to fill in the gaps of the trajectories. Then we have the maritime event detection component. This is the one that we have, the infrastructures that we have in our premises. We have a batch layer that is able to distributively process AIS historical information, and we combine this with a real-time layer that is able to process in a distributed way multiple streams of AIS data. And we do all this in order to be able to derive events So the simple events are the events that are building blocks of more complex events. So examples of simple events that we are able to derive are turn events, acceleration events, route deviations, when a vessel navigates into shallow waters, proximity events, when two or more vessels are too close together, and last but not least, an event that is triggered when a vessel goes off AIS coverage or intentionally switches off its transponder. This is the AIS off event. So once we have the simple events in place, we are able to combine them to produce more meaningful complex events, like, for example, the legal phasing event. So here we use the event for forecasting system of NCSR. Elias will explain that later. And we have a simple rule that takes into account navigation information about vessels, like, for example, the speed. So in case the speed is in the range of the typical speed of fishing vessels while they are fishing. And we have an event type IIS off. So when a fishing vessel has switched off its transponder, it's very likely that it is about to perform an illegal phasing event. So here you can see also our visualization component that shows the complex and the simple events that we are able to derive in real time. So I think that's it. I hope I didn't take too much time. So thank you for your attention. And I think the next one is Elias.
Gabriele.
Gabriele, yes, sorry.
Share. Second. Do share. Okay. Hi. Do you see the screen?
Yes.
Yes.
Okay. So good afternoon. My name is Gabriele Ferri, and I'm a research scientist at the NATO STO Center for Maritime Research and Experimentation in La Spezia, Italy, and I will talk about the development of a robotic hybrid network for coastal surveillance that is part of the INFOR maritime use case that Costantina was talking before. Okay, so this is a picture of the use case that we are developing and we are going to test in February here in La Spezia. The objective is to create a synergy between global and local view sensors for a MSA application. The objective is to create a way for multimodal smart sensing and data fusion to support the decision maker of the system. As you can see, the system and the use case will be divided into two different kinds of sensor. We will have a global view sensor. Mainly, we are analyzing during this work data coming from the Sentinel multispectral instrument and SAR from the Sentinel satellites, and data produced by the AIS from the vessels. The first objective of this sensor is to provide a global view of the area and to cue in some way the robotic network. And then we pass to the local view sensor, in which we will have a local robotic network. I will talk more about this in the next slide, that in a cooperative and autonomous way detect and track the target and sending information to the INFOR system. There will be also a fixed thermal camera to work in cooperation with the robots. This information will be fed into the INFOR MSA and decision support platform for the complex event detection. For example, if the vessel is fishing in an unauthorized area. To focus on our network, on the network of hybrid robotic network, we have to say that the idea for MSA application is to use a network of silent, long endurance, cooperative, passive sensing robots. Passive means that you hear for the acoustic noise produced by vessel. That will be composed of liquid robotics wave gliders that are surface vehicles, as you can see here, that move exploiting the power of the waves, and OEX-C autonomous underwater vehicles. You can see them here. The objective is to create a way for early, stealthy vessel detections. Obviously, they will be silent. They will be not visible because they are underwater and the surface vehicle are very low on the water surface, and to offer a persistent coverage of an area. Robots will share data fusion and will cooperate with the onshore thermal optical camera. But we have to say that the robots have limited speed and also bearing only measurements, because in the passive sonar, you only measure bearings to the target. To cope with this, we propose that cooperative autonomy, in particular autonomous decision-making and data fusion, are the key driver to improve detection, classification, tracking, and localization performance. But how to do this? To do this, we have developed an occupants grid mapping framework that is the basis for cooperative behavior. We've started from data from one sensor. Here you see test at sea that we have done with the Perseus sensor. And from the sensor, we produce position and bearing measurements. And with that, we have developed a framework of occupancy grid map that produced these occupancy maps. What is an occupancy map? Occupancy map is a map in which each cell shows the probability that a target is at a certain location. As you can see here, you have a beam or yellow area. A beam because the measurements are not a location measurement, but are bearing measurements. So you have a beam of possible location of the target. So we use data fusion between the local map produced with the measurement produced on board by the vehicles and the remote map produced by the measurement received by the collaborators to produce a fused map. And we compute here, we make some computation, in particular the Laplacian, and we search for low value of this Laplacian. And you see here, this is the position of the target. Once we have this perception layer in terms of area, this is a world model that drives our decision, we can make decisions. So we propagate these maps into the future, supposing different decisions of the robot and different possible measurements, and then we select the best decision to create the most suitable geometric configuration and the most suitable configuration from what concerns the probability of detection of the sensor. This is what we have tested here. You see here the two robots, robot 1 in black and robot 2. This is the sensor footprint. In front and back of the robot, we assume a probability of detection 0, is called to the hand fire, as we say with the linear array. And here is the target, the estimated position, the square green, and the true target position. The target is doing a sort of rotated square. As you can see here, the cooperative target localization behavior is active. So the robot starts to follow the target, that is moving to the northwest. And when the target turns to the northeast, the target number 1 turns to east to keep the target towards broadside to enable data fusion. So we compare this with a movement, horizontal movement of the two robots, that is without autonomy, without autonomous decision, and we compare the two results. Here at the top, you can find the probability of detection in the two cases, in red with the data-driven behavior and in black with the racetrack. And as you can see, in red, we keep a probability of detection high, even if we have this area to 0. This means then the target that is faster than the sensors move inside the end fire, so a probability is 0. But the movement of the robot enables the robots to reacquire the target, while with the black one, with the racetrack, at a certain point, the target becomes 0 because the target goes outside of the footprint of the sensors. And while below, is the error and localization. We see while in red, again, is data-driven behavior, the error is limited. In black, at a certain point, you see the error becomes high because the sensor cannot see the target. So here we show how the autonomous decision, cooperative autonomous decision, can improve the target localization and the acquisition of information on the target. And here is a typical scenario, and this is will be the base of what we are going to test in February. So we have a ship that at a certain point the ship change its position, and we have a first simple event detection, for example, AIS switched off. This cue the robotic networks, the local network, with an area to be surveyed. The robot move, the camera look at the area, and we start to collecting information and to pass this information to the enforced system for the final complex event detector. For instance, that the ship is fishing. And how to bring everything at sea. So to do that, we are using and we have worked on the ICADME cooperative autonomy framework. That is a task-oriented autonomy. This is the architecture that runs on our robot, and then we will have a multitask mission composed of the area survey task and a target localization task based on the occupancy grid that I've described. Bringing everything at sea is not simple because, above all, if you consider below the water operation, the big issue, key open research area is the problem in communication, because you talk with using acoustics, so acoustic modem, and the acoustics is very complex. So the amount of bandwidth is limited. Just to make an example, more or less 60 bytes per second, so nothing respect to the above the water communication. And then the communication is also intermittent because you may have packet loss, so it's very challenging. For this reason, we developed a communication redundancy scheme. The idea is that in each message we have encoded, trying to spare bits, encoded the contacts from different files into the past. In this way, even if we have some packet loss, we try to cope with that. We tested that during Dance 20, our last trial. So in this trial, we have our alliance, the ship, detected as the target to be detected, and also as the command and control system. And with two AUVs, that is Groucho and Harpo, they were the sensing asset, and they were towing linear arrays. So linear arrays working again in passive, as I was saying before. So working in passive, we have bearing-only measurements, but we have also another feature that is right-left ambiguity measurements. It means that when you have a linear array and you cannot establish if a measurement is coming from right and from left. So every measurement that arrives, you create two measurements. And so you have to understand which one is the correctly related to the target. For this reason, we use a multi-sensor fusion to tackle this detection and localization problem. And we had the ICADME controlling the robots and using the occupancy grid framework I was describing before. So ICADME was running on each robot and also on the ship. And the robots exchange the bearing contacts, the position, and also with the ship. So the maps were created in real time on the ships and also on each robot. So we had three different fusion centers. And we tell these were the result. You can see here the local map. These are results computed from Groucho. So these are the real-time results from Groucho UV. Here you see the trajectory of Groucho in black and the trajectory of Harpo in red, and these are the bearing measurement. As you can see, there were some noise. Here is the local map. It is the map computed by Groucho with its own measurement, and this is the remote map. That is the map computed by Grazio with the Harpo measurement. And this is the fusion. So this is the Laplacian. So the white, high white is where you assume to be the target. And you can see here, this is the estimated target position, the real position, and this is the target estimated position. So very, very, very close. After a while, the ship moved. And as you can see here, the system was able to detect that. You can see here, this is the magenta circle, the estimate position. And we were able, the system was able in real time to track and detect the target. To conclude, so the concept of hybrid robotic network has been applied to the MSA use case of the INFOR project. The objective is to develop a pervasive, persistent, and scalable monitoring system to provide an effective local view. This is essential to support the decision maker activity. As I said before, autonomy and networking are recognized as the key driver to deploy this kind of system, because to manage and to handle at sea in an effective way robotic networks, we have to rely on the intelligence of the nodes. And as a next step, we will conduct the INFOR pilot site trial in February 2022 here in the La Spezia Gulf. And to conclude, the INFOR MSA use case demonstrates how the synergy of remote sensing, machine learning, big data, and autonomous robotic networks can enable the development of new generation of systems in terms of surveillance systems that are more persistent of traditional means and very effective to support decision makers. So these are the references. Thank you for your kind attention. And I will leave the stage to Elias that will talk about the complex event detector. So thank you.
Okay. Hello, can you hear me?
Yes.
Okay, let me share my screen. Yes, you can see my screen, right?
Yes.
No. Okay, so I'm going to give a brief talk about the complex event forecasting module that we are developing in the context of the INFOR project. So let me first explain a couple of things about complex event forecasting. So we're talking about forecasting of complex events. Konstantina already mentioned something about it, but first of all, we need to understand that there's not much work going on in complex event forecasting. There is considerable work in related fields like process predictions, as you see here. There are tens of papers devoted to this issue of predicting the outcome of processes, of business processes. But in the field of complex event recognition, forecasting has not received much attention. And this is the gap that we're trying to fill here in the INFOR project. So what is exactly complex event forecasting? So the general idea first is that we are dealing here with streams, real-time streams of events. You see here on the left-hand side of this figure with the green color, a stream of simple events coming into our system. These could be AIS messages or whatever other events of interest. In the maritime use case, these would be possibly AIS messages. And we also have here down here a set of complex events, definitions of complex events. You see here an example here of a pattern written SQL-like language. So we have a set of such patterns here, and the initial goal is to detect upon this stream of input events to detect instances of satisfaction of these patterns as soon as possible. So with minimal latency, and the outcome, the initial outcome is another stream of complex events. Now, this is the idea of complex event recognition. Now, if we want to go beyond that, and try to perform some forecasting, what we would like to do is to also produce another stream of forecasts. And what do these forecasts tell us? They tell us whether, if and when a complex event as defined by such patterns will be detected by the engine here before it is actually detected. And you can imagine here very obvious patterns that we would be really interested in forecasting them. For example, collision of vessel collision. I mean, if you can forecast that some vessels are on a collision course and they will collide if no action is taken, then this would be very crucial, and we could inform authorities about such critical situations. And now moving on, the thing I'm going to present some technical details in the remainder of the talk. So first of all, let me say that there are different ways to define event forecasting. So we could also, by event forecasting, could also mean input event forecasting, that is trying to forecast the input events themselves. What are they? So for example, is a vessel going to have a speed of a certain level or not? This could be classified as input event forecasting, but we are mostly interested in complex event forecasting. As I said, we are trying to forecast, first of all, if a complex event is going to be detected, and this you can view this as a binary classification problem, where you emit, yes or no answers. So this is a classification problem, and on top of that, we might also want to try to estimate the time that the future complex event is going to occur. And you see here, this could be viewed as a regression problem. So these are the different formulations of the event forecasting problem here. Okay, so where do you start? Let's say that you are convinced that complex event forecasting is of some value, and the question now is, where do you start? So we need, first of all, we probably need a probabilistic model, right, for this. But the problem is that in complex event recognition, there are many different formalisms and models for defining and detecting complex events. So we need to start with something simple, and this is also for presentation purposes. Let's start with something simple. Let's assume that we define patterns in terms of regular expressions and automata as we know them from introductory CS courses. And okay, so a pattern is defined as a regular expression. We assume that the stream is just composed of symbols, A's, B's, C's, and stuff like that. And so we define a pattern as a regular expression. And what we want to do is, we also assume that the stream is generated by a Markov process and with Markov dependencies. And so what we do is we consume these event streams and forecast when this regular expression is expected to be matched. That's the idea here. And we are also trying to revise these forecasts. As we receive more and more events, we're also trying to revise these forecasts. So this is the general idea. And this is a very simple example here. Let's assume that we have a stream composed of A, B, and C. These are the symbols. This is the alphabet, let's say, from which you can construct an event stream. And this is, let's say, a very simple regular expression, a pattern defined as a regular expression, where we want an A followed by C followed by C. And this is what you would get as an automaton here, right? And you could actually map this automaton into a Markov chain like this down below. And this transformation here in this example assumes that we assume that the events are identically distributed, independent and identically distributed, but there are ways to overcome this. The general idea, though, is that you have a regular expression, you can get an automaton like this, and you can convert this to a Markov model like this here, a Markov chain in this case. Now, if you do this, then you can, sorry, let me go back again. The idea in this case, what do we mean then that when is a complex event detected in this case? In this case, a complex event is detected when the automaton reaches the final state here. Every time the automaton reaches a final state here, then this means that a complex event has been detected. So what do we need this Markov chain here? We need this Markov chain here in order to estimate, given that the automaton is in some other non-final state, 0, 1, or 2 here. We want to infer in how many steps or hops or events it will reach this final state. And this is exactly what we are trying to do. We are actually inferring when the complex event is detected. So this is the general idea. And so if we can train our automaton to give us a Markov chain, what can we do then? For each one of its non-final states, we can derive a distribution, a so-called waiting time distribution. You see here, for the 0th state here, the red state, you have this red distribution here. For the state number 1, the green state, you have this green distribution here. And what do these distributions tell us? They tell us the probability of reaching the final state in k hops from the current time, let's say. So for example, here, if I am in the 3rd state here, in state number 3, so this magenta distribution is activated, let's say, and this tells us that there's a probability of around 70% to reach state number 4 here in one transition from now. And there's a 0 probability to reach state 4 in 2 transitions. Why this is, you can see why this is the case, because there is no path from 3 to 4 with 2 transitions, and so on and so on. So you can do this for multiple values of the k, let's say, variable, and you can do this for all the non-final states. And this is what you get. And once you have these distributions, you can derive the various kinds of forecasts. For example, you can derive this kind of interval forecasts, as this interval is shown here, this red interval. This tells us that if I am in state number 0, I have a probability of at least 50% to reach state number 4 in 5 to 12 transitions from now. This is what this tells us. So this is the general idea of how you can take a regular expression, use it to perform complex event recognition on a stream of symbols, so a simple stream, and then convert this to a Markov chain and derive some forecasts. Now, as you can assume, there are some limitations with this formulation. So, as I said, input events are simply symbols, so they are not really events. And this is why we use classical automata. What's the alternative? We can use more powerful automata and expressions for this purpose. One of these models is the so-called symbolic regular expressions and symbolic automata. And we can also use, instead of just mapping the automaton to a Markov chain, we can use more advanced statistical models like variable order Markov models, and these models have this nice feature where they allow you to remember only what is informative. So if you want to remember to have some memory before making a probabilistic inference, you have, first of all, you consume streams, and you want to make probabilistic inferences on these streams. So how do you do them? You do them by looking back into the past and what has been preceded in the stream in order to make some inference about the future. So these variable order Markov models allow you to go deeper into the past. This is an example of how you could possibly write a symbolic regular expression. You see here that this is significantly more complicated than classical regular expressions. And you see here that you can actually write, you can actually use various predicates. You can query the messages that you get for extra information, like for example, if we assume that we know we somehow the message that we get have some information about the type of the vessel, we can also write predicates like this one about whether a vessel is a fishing vessel or not. And we can combine predicates with Boolean operators and write patterns like this one. And okay, it is more complicated when you write it, but of course it provides you with more expressive power. And it usually leads to automata that are more compact. And the good thing about symbolic automata is that you can still use such techniques about, either mapping them to a Markov chain or using variable order Markov models. So they have nice mathematical properties, and so you can use them pretty much, not in exactly the same way, but pretty much in the same way as you use classical automata and Markov models. And so, yeah, just a very simple example here of what variable order Markov models are. And we use, in Infor, we use a specific type of variable order Markov models that are called prediction suffix trees. And I will explain very briefly what these are. So let's assume that you have an automaton like this. This is presented here as a classical automaton. You see here on the transition symbols, but this is done just for presentation purposes. You should assume here that on the transitions you have Boolean expressions, but for just for presentation purposes, let's assume that we have symbols here. And this here, on the bottom part of the figure, you see a prediction suffix tree. We can use a training string to learn such a prediction suffix tree, which basically tells us what we can expect with what probability given some specific context. For example, in this case, if you, let's use this left node here. This node tells us that if I have seen two A's in the stream, then the probability of seeing another A is 0.75, and the probability of seeing another B is 0.25. And this is what prediction suffix tree looks like. And the interesting thing here is that the depth of the nodes of the leaves is not the same, right? So for some it is 2, for some it is 3, depending on how informative its node is, you expand it or not. This is why they are called variable order Markov models. And okay, I'm not going to go into much detail about this. The point is that you can use this tree and this automaton then to estimate the probabilities of various paths. This tree here shows you the various paths that the automaton, this automaton here can follow and their probabilities, and you can just use this prediction suffix tree and the automaton to derive this tree of future paths and then be able to make inferences about the future behavior of the automaton and about when and if it's going to reach this final state here. And just the last slide here just shows you a couple of figures to show you how you could use this complex event forecasting functionality. Let's assume that you have this kind of area here in the sea, and you have a vessel, and you want to know whether this vessel will enter this area or not. Okay, and these arrows here are positions from the same vessel at different times, at different points in time. And you see it follows two different trajectories, this one here and this one here. And so you see here that as the vessel moves on, so this trajectory stays outside the area, this trajectory goes into the area, and you see here that the system informs us here. It has learned, first of all, it has learned that this trajectory will never cross the area and it does not produce any forecasts. And this trajectory, on the other hand, enters the area and it starts producing forecasts. And this is one way to visualize them, right? Showing an arrow here, and dark red means that there's a higher probability of entering the area. And you see here that the system has learned that this trajectory will enter the area and produces forecasts. And that's all for forecasting. Thank you very much.
Thank you, Ilya. Thank you all. So this now the time for questions and answers. If you have any questions, please post them at the chat. I haven't seen any questions yet. So maybe it's important to mention that all the components of the Infor architecture will be made available open source. And actually the streaming extension that's led by RapidMiner is already available, and maybe Fabian can show the viewers where they can find it and use it.
Yeah, I can do it. There are no questions so far. Maybe we can start with that. So just let me share the screen. RapidMiner Studio is available for free to download in its free version. We can utilize all functionality, and then you can always go through the so-called RapidMiner Marketplace, which is also free to download, free to use, where you can use the search engine searching for the streaming extension, which is, as I called, the prototype of the Infor architecture, and you can download it and add it to your package and can utilize the functionality I have shown here, as you see. Then you have this additional operators which you can utilize to actually deploy your streaming processes.
Okay, thank you. So I don't see any questions so far. So if you have any questions, don't hesitate to contact us, either from through the website of Infor, or basically you can see the information that is available and our presentations. We'll be happy to also to collaborate with other projects in common and targeting common goals. And I don't see anything else, any questions so far, so maybe we can finish the session right now. Thank you all for attending the session, and I hope that you have a very nice, informative eBDVF conference. Thank you. Bye.
Hi, thank you.
Thank you. Bye.
Bye.
Goodbye. Bye.
Okay, so let's start this presentation about the Cloud Button project, and it's called Serverless Data Analytic Platform. So let me share my screen and I will introduce you to the toolkit that we have developed in this talk. Petra told me you are a little bit tired, so I want to get you excited about this, and we will try to make it like very interesting for you guys. So, okay, what we are presenting today, it's me, that I am full professor at URB and coordinator of the cloudbutton.eu project. Josep Sampe could not attend, so I will present his part. Then Gil Bernick from IBM and Tristan Tarrant from Red Hat. So, Cloud Button project. So the Cloud Button project is in this big data call, and this is a project where the main technical leaders are IBM, Haifa. It is also Imperial College London. It is IMT in Paris, and it is Red Hat. And we also have some use cases like the European Molecular Biology Laboratory in Germany doing metabolomics, the Hatton Institute in the UK doing genomics, and the Matrix Foundation doing geospatial data. So the main goal of this project is to democratize big data by simplifying the overall life cycle and programming model of big data applications thanks to serverless technologies. So this is a big aim. So Cloud Button wants to democratize big data. We want to make it super simple to data analysts that are using the cloud thanks to these novel serverless technologies. And we are going to demonstrate this in this super big data with high volumes that are genomics and metabolomics in bioinformatics and geospatial data, so LIDAR and satellite data. So these are big aims that we had 3 years ago, and we will show our results after 3 years of development. So why we name Cloud Button Cloud Button? And you see this text from this Berkeley paper, this Occupy the Cloud, where this professor from Berkeley said, why is there no Cloud Button? And he outlined how his students simply wished that they could easily pass a button and have their code existing, optimized, single machine code running in the cloud. And this inspired us 4 years ago to say, we want this Cloud Button. Push the button and have your code in the cloud, unmodified. And here others have followed this inspiration. And you have Tim Wagner in this blog post called The Serverless Supercomputer, telling this, what if every developer had access to the world's largest supercomputer? The cloud as a super big computer. Or this from any scale. Developers want the development experience of the laptop with the power of the cloud. They want an infinite laptop. So why if I could code my laptop, but then have infinite resources in the cloud? And that's precisely what we want to achieve with Cloud Button. It seems heavy, but I think we have something interesting to show you here. Well, for those of you that are not very aware of what serverless is, I must say that serverless is a platform, this definition, you can find it in this paper, is a platform that hides server usage from developers and runs code on demand, automatically scaled and built only for the time the code is running. You will probably know platforms like Amazon Lambda or Amazon S3 or IBM Cloud Functions and IBM COS. These are serverless services that are automatically provisioned. You don't have to provision their uses. You pay only for the resources you are using. They auto-scale up and down, up, very up, like thousands of cores, and down to 0. And so they are elastic, so they can adapt to your workloads very easily. So these kind of characteristics are super good for parallel programming and parallel computing of big data. Here, I'm showing you why serverless for big data. And you see here 2 interesting plots that we did with our platform. You have here the link. And we launched 1,000 parallel jobs that are compute intensive at the same time. In less than 100 milliseconds, we have 1,000 virtual CPUs processing data obtained from object storage. And what is incredible is you have a lot of computing power instantaneously, and when it finished, it stopped billing you, but also the aggregate bandwidth that you can obtain from these functions to object storage. You can process 100 gigabytes per second. So this is the serverless supercomputer. We can process huge amounts of data very fast. And then what we have done is to create a serverless big data toolkit that is called Lithops. And we are going to explain it now about this. And I want really you to understand the difference between serverless design and cluster computing design. So you probably know another toolkits like Apache Spark, like Dask, like Rai. They are cluster computing systems for big data, unlike Lithops that has a serverless design. And what is the major difference here? With these cluster computing technologies, you need to statically provision the resources that you need for your cluster. They don't scale fast. So you normally, if you require 5 nodes, you program and configure these nodes. You can, of course, have over provisioning or under provisioning if you don't know the resources that you need on advance. On the other hand, with Lithops and our serverless approach, we do it on demand. We create a cluster of the need that we need in the moment, the entire cluster, and we scale that to 0 in each moment. So this is really serverless, not having a cluster that scales a little or down progressively. We have 0 configuration on the file resources. So a data scientist with no knowledge about cloud and cluster can just program a Python notebook and run applications on top of thousands of virtual cores. Not like here where you need a backend engineer to configure your cluster. So in our case, also it's important, it is data driven. So we automatically provision resources based on data from object storage. In a cluster, you normally ingest, then compute. You load all things in memory and you process it there. So then in our approach, we are very good for some cases of embarrassingly parallel computations, data preprocessing, Monte Carlo simulation. I have many examples here of data management and crunching from functions to object storage. And it is super good for elastic workloads. Gil from IBM, he will show you some metabolomic pipelines that you cannot predict. And if they are very elastic in a cluster environment, they will over provision or under provision, things that they cannot do. Also, the fast startup of our serverless resources make our approach suitable for interactive workloads. Whereas cluster computing is normally designed for batch analytics. So let's go to explain now what is this Lithops thing. So Lithops is the major result of the Cloud Button Toolkit. This is not a research prototype, guys. We have 4 years of development with research engineers from different institutions, from IBM, from universities. I mean, Lithops is in production now in many environments, like EMBL, banks, metabolomics, and different companies. So it is, you can use it already now, and it is mature software. Lithops can be defined as a multi-cloud Python computing framework that allows multi-threaded local applications to be scaled to massive cloud resources. So you code normal Python in a notebook, and when you launch processes, it is launching functions or resources in the cloud. So here, the difference is that we don't require any configuration or provisioning. You just say you configure your credentials to your serverless services, and that's all. You can access these resources in this link. It is completely open source, so it's free of use. More characteristics. One is transparency in cloud computing. And what is transparency? Is that we are using identical operations for local and remote resources. This is the infinite laptop. You code a parallel application in Python, but it is scaled transparently to all the resources in the cloud, so it can scale a lot. And this is without configuration of the serverless resources. And also, this is multi-cloud. We want to avoid vendor lock-in. So the same code that you are running will run in different clouds. And I will show you now all the backends that we are supporting, but you change a very little thing, one import configuration, and your code is changing, running identically in another cloud provider. So we created an extensible architecture to support this, and you will see the list here, it's impressive. We support compute and storage services in many clouds. So we support, for example, AWS Lambda, AWS Batch, AWS EC2 virtual machines, and we support S3. But we also support COS, Cloud Object Storage in IBM, and Cloud Functions or Code Engine, or Azure Functions and Azure Blob Storage. And the list continues here with Google and Alibaba. But Lithops can also run on-premise. So we run on top of Kubernetes and Knative, and we run on top of OpenStack. And as storage, you can use Minio, Object Storage, OpenStack Swift, Redis, Infinifan, Ceph. So you can also deploy this on-premise and combine it with cloud resources if you need them. Lithops, it is very easy to change provider with some minimum configuration files or information that points you to the storage layer and the compute layer that you are using. And only changing that, this simple Python code in a notebook will run when you say, for example, here, pull map. We are launching this function in parallel, and we are calculating something. This P calculation now will run in the cloud with the number of processes that you want. And this code is very simple. The characteristics is that now Lithops code, the main program, will orchestrate all these pool of workers that we use in the cloud, either using serverless functions in Amazon or any other cloud. So it will be transparent for you. An example that I always explain is that in EMBL, before they used Spark and they had a backend engineer and a front-end engineer. Backend engineer for configuring the cluster, front-end engineer for doing the data analytics. Now with their front-end engineer, they can create Python nodes with Lithops that run over these cloud resources. And the nice thing is elasticity. In many cases, and Gil will explain that, where your pipeline has tasks of different parallelism, so we have an elastic workload that here I need 5, then I process this data, I crunch this data, and then I need huge parallelism, like 1,000 cores. I do it, in the next stage, I need 100. This kind of pipeline is very difficult to solve with cluster computing technologies, because if you provision the cluster for 1,000, that is the biggest one, you are over provisioning, because in all these stages, you are wasting your resources. With Lithops, you will create 5, then 1,000, then 100 dynamically. And this is very good where your workload is elastic, or even you don't know the resources that you will need. How does Lithops work? So Lithops, basically, in the phase 1, he takes the classes and variables in Python and transfers for you to the cloud. You don't configure containers or anything. You just code a Python code in your notebook. Then in the background, Lithops use object storage to store this information in the cloud. It delivers it to the function, it deploys, and it runs. We have a storage backend that is the object storage, and we have the compute backend that are the serverless functions or the container infrastructure that you are using. Then each worker of the serverless receives the location of the data, it will retrieve it, it will execute it, and then when the execution is completed, the workers will store the result, and the executor module, that is the Lithops runner, will obtain the final resources that you need. So this is the overall architecture of Lithops, that it's transparent of you because you only see a Python notebook. Lithops is very good design for embarrassingly parallel jobs. So if you want to parallelize something like a hyperparameter optimization, Monte Carlo simulation, data preprocessing, web scoring, a lot of these tasks are perfectly suited for Lithops, and Lithops can do more than that. We have in our webpage a lot of use cases and demonstrations of that. And it's extremely good for big data processing that it's in cloud object storage. So Lithops marries cloud object storage with cloud functions. So you have this serverless supercomputing that benefits a lot from big data stored in this object store. And Lithops is integrating data discovery and partitioning in a transparent way. And this is very important, data-driven. So we spawn resources as needed depending on the data volume. And this is because we have created data partitioner for different formats that, for example, with our APIs, we offer a MapReduce API, a Python multiprocessing API that transparently accepts CSV, text file, genomic data, compressed data, metabolomic data, geospatial data in TIFFs and LIDARs. And we have created a lot of partitioners. And this is really the powerful part of Lithops. When you execute a map function that processes data in parallel from a bucket in object storage, the nice thing is that you just point to this bucket and you just say, for example, here is the sample hello world in big data, word count. You say here, I want to process my map function over this data location. But if in this data location, you can have 1 gigabyte, 100 megabytes, 1 terabyte, or 1 petabyte, whatever you want to put there. I mean, the code is not dependent, it's not task-centric. We are not telling you how many processes you will need or how many resources. We create chunks automatically from this data that go to the required functions. So the data scientist does not have to bother about the resources. He simply say, I want to process data in this bucket, just launch the processes for me, Lithops. And we are doing that. So this is why we are data-driven. You don't have to tell how many processes do you need or configure your cluster. And that's why we are doing this data-driven partitioning. So we have, of course, formats that need pre-processing, like LIDAR or IML set. This we have to launch a previous chunking algorithm to leave it there in buckets. But we also have very interesting on-the-fly partitioners, like for CSV, for text, but also for compressed data. With genomics data, we have nice experiments where you have a lot of compressed data. And because Object Store enables you to obtain ranges of data, you don't have to have the data already chunked or partitioned. You have all the data set in your object storage, and our functions will partition it out automatically, even if the data is compressed, to give it each function the information it needs to operate. So this is super important for many use cases that we are using. As I said, genomic is one of the most data intensive that we are using, but I wanted to explain you here about one special use case, that it's geospatial analytics. Geospatial analytics, it's also using big data obtained from either satellites like the Sentinel European satellite or other sources. In this specific pipeline, we calculated NDVI, that I will explain what is, that it's a calculation of the vegetation index in an area. It's useful to calculate water consumption or wildfire prevention. So this kind of climate change things, we can help to do this with our technology. So, for example, there is some data from Sentinel-2 mission. This satellite is monitoring the land and it's creating high quality images that are available since June 2015. And even Amazon makes it available in an AWS S3 bucket. So this information is public. And we are going to show an example where we are using this information, these maps. So basically, data from this Sentinel satellite is captured in different products, and each product is covering an area of 100 kilometers squared. And each product is including all this information about in different bands about the captured information, like the blue bands, the green bands, the red bands, the vegetation, read edge. Well, I'm not going to give you a lot of technical details about this geospatial pipeline, but you have a lot of information that the Sentinel satellite is giving to us. What happens to this Sentinel data? It is astronomically big. It's very huge, and it is very difficult to analyze this data if you don't have a lot of resources. This is also happening in other environments like genomics. For example, genomics, the data is growing so fast that you cannot have it in your own cluster. The UK Ministry of Health has moved all the data to Amazon S3 and to object storage, because object storage in the cloud is the only platform that can host all these amounts of data. So you need tools to process big data in object storage. And our Lithops approach is ideal for dealing with these huge volumes of data in a data-driven way, so adapting to this. So here we also use some optimized geotips that Google is providing. They did some calculations on top of the original tips information. So now the nice thing again is that now Amazon is doing the partitioning for us. So now these geotips enable to split this product in 11 tiles or sub-images. So now we can launch parallel functions for each of these partitions in the geotip. You can also access, this is also public information. And then if we can launch parallel functions for each of the parts of these tiles, we will be able to process dynamically in a data-driven way a lot of data. So here we have the task that we want to accomplish is this NDVI calculation. This normalized difference vegetation index is well known in geospatial environments. It's a simple graphical indicator that can help us to observe leaf green vegetation. For example, when you are observing fires or climate change or water usage in some zone. To calculate that, we need 2 bands of the spectrum that Sentinel is giving us. And here you have the code. Of course, we publish everything in our website in Lithops as open source, and you have tutorials, you have open documentation, and we are going to publish, and we already have, but we are going to publish all the big data pipelines of the project, genomics, metabolomics, geospatial pipelines. We are publishing it in the cloud, so you can use these examples to learn and use it with big data and see how they are working. So mainly, I'm not explaining all this code, probably it's complicated. This goes to a Python notebook. As always, you configure where are you using things. Like, for example, I'm using Lambda here, I'm using S3. And then to access some data. So basically here we have very simple. I have a map function that calculates DVI and DVI data on this ITER data, that it's the bucket where we have the information. We will compare 2 dates to see the differences between 2 areas using this NDVI calculation. This is the code that goes inside the function that takes 1 chunk of data or 1 part of the image, and it will calculate for you this vegetation index. And as I say, this is data-driven. You don't tell launch 1,000 functions, 100. Lithops adapt it for you because he just takes the information from the bucket and launch the required resources. So here, you, for example, see the output between 2 areas. We calculated in California, there were big fires in the summer. And we could see here before, after, and this calculation in September 2019, September 2021, 2 years after that big fire. We see here all this green that now is not here. We see here some water areas that are not here. And here we plotted the difference between the two to really know what has changed in this time. So basically, what we did with lithops is to calculate the NDVI difference between two dates. We analyzed 18 packages. Here is a simple example for you, studying 2 bands, and we analyzed 9 gigabytes. We launched 1,000 functions in parallel that could process this data in 20 seconds. So you see here the potential of lithops. And I must say, what are the benefits of using lithops for this? First of all, simplicity, productivity. I mean, you can have data scientists that are not experts in cloud. This is democratizing big data. They create a simple notebook and they run it in their computers. And in reality, when they say map, they are accessing massive information in the cloud, in this serverless supercomputer, and they are launching a lot of compute cores in the cloud that are resolving that for them. So the productivity and simplicity are important. The data scientist, he doesn't need to understand the provisioning of resources because the lithops is data driven, and it is using simple Python code. He doesn't need to learn anything about this, or only understand that data is in the object store and that computing is there. And he can even run it locally to check that he understands it with small data and then run it in the cloud. The other advantage that it's not only simplicity, productivity that are important for democratizing the cloud, this idea of the cloud button, no? They push a button and you have your local code in the cloud. This is the simplicity of pushing a button, but also the performance, scalability, and elasticity. So, I mean, in which other environment you can run 1,000 parallel cores that obtain data in parallel from the object storage at this speed, and they will bill you only for these 20 seconds of computation that you run. And I must say, performance, this is a scalability. The amount of data that you can process is huge. And the pay per use is very interesting to generalize to other environments. So now Gil is going to show you another interesting use cases like metabolomics and others, where IBM is using lithops in production. I mean, we have developed during these 4 years this project, and now is well tested. So I finished here now. I gave you a general description of what lithops is, and now I let you, IBM and Red Hat, that are our industrial partners, show how they are contributing and using this platform in production environments. So I finished here. Now it's time for Gil to take the lead. So I stop sharing, and Gil, you can start now.
Okay, so let me share it. Okay, so thank you very much. So my name is Gil Wernick. I am from IBM Research, and I'm going to continue where Pedro stopped. So first of all, just to remind, so lithops fits into many use cases, data preprocessing for kind of machine learning, deep learning, because they all require to do some data preprocessing prior it's used for machine learning. Batch processing or all kinds of workloads that embarrassingly parallel, that you can map your workloads into parallel tasks, and then every task executes something, and then they have results, and you obviously can have in multiple stages. So you just run lithops with many tasks, and then your lithops collect all the results, intermediate results, and then you run your calculations again on the results, and so you can have so multiple stages. Now, in particular, I'm going to to show you the metabolomics use case we developed in Cloudbutton and also the lessons learned from it. Okay, so the spatial metabolomics, it's an interesting field of research. They basically know, you provide them all kinds of medical images, and they know they're using some proprietary algorithms, and they know how to detect all kinds of anomalies in those huge medical images. And then they know also how to identify very small regions where those anomalies exist. And so this benefit to understanding health, disease, cancer, or all kinds of other issues. And this is very interesting field with a lot of growing interest. And now, but from computer science, it's also very interesting use case because it's a pure big data problem. So the process when they run those algorithms to detect anomalies, so this process consider every pixel as molecules, and then they have thousands of molecules in a pixel, and then they also know how to shift those molecules. So eventually, this process of processing those medical images generates huge amounts of resources that you need to run those algorithms. And so you obviously can't run it on your laptop, or you can't run it on some good cluster. So it's very challenging how to make it efficiently. And the use case we work was the Metaspace use case. It's Alexander's team from EMBL that they developed a tool that they call imaging mass spectrometry application. And this application works like this. So a customer uploads some medical image, and then he chooses some molecular databases. It might be one, might be more than one. And now there is those proprietary algorithms that they developed, they are running, and they try to identify all kinds of regions in this medical image that have anomalies, what kind of anomalies. So there are lots of compute resources required here, and it might take time, depends on what type of the image and which molecular databases you choose. And then eventually, when this process is done, so it will generate output of small images that contains regions from the initial medical image, and those small images also try to imply what kind of anomalies the process discovered. And this is how it works on the general level. Of course, there are lots of algorithms and lots of processing that happens in the data preprocessing and molecular scan, but that's not the scope of this talk. Now, before Cloudbutton, before we met this team, so they used Apache Spark cluster on top of, and they deployed their application there. And it didn't work well for them. Now, there is obviously nothing wrong with Apache Spark. Okay, Apache Spark, it's a very popular, I'm sure everybody familiar with it. It's very popular big data engine, and you can do lots of things with it. MapReduce, SQL, even machine learning. It also contains advanced capabilities to process all kinds of big data workloads. And Spark is a cluster. So if you decide the size of your Spark cluster, then it's very easy to install Spark on this cluster, and then you can use it for all kinds of big data workloads. But the challenge with Apache Spark in the Metaspace use case was that they also had many proprietary algorithms that they had to run. So they had to run a lot of software stack on top of Spark. And once you don't use Spark advanced capabilities that comes with Spark, but you only use Spark to deploy your proprietary codes, then Spark became a bit less optimized for this. And it may lead to all kinds of issues like less optimized RDDs in Spark, and then they have byte dependencies, and maybe they're meti shuffle, and there are lots of broadcasts. But in particular, a challenge for the Metaspace use case was that they actually never knew what size cluster they need. So the normal way you work, you start your Spark cluster, then you deploy the workload, then you run it, and you finish. In case of Metaspace application, they never knew in advance how much resources they need, because the algorithms also generated data during the algorithm's execution. So it's not enough to see the input size of the medical image and the input size of the molecular database to figure out what Spark cluster you need. But basically, you need to start running their workloads, and only in the middle of the execution, you will know what size cluster you actually need in reality. But that was too late, because you already provisioned Spark cluster, and this resulted in less optimized way Metaspace worked. So either you provision Spark cluster, but then in runtime you realize that the Spark cluster is too large, so you pay more, it costs you more than it actually needed to be. But even worse, if in the middle of execution you realize that the Spark cluster is small, then it's a bigger problem, because then the workload became very slow. It may run hours and hours, and then it may even collapse at some point. So, so the challenge here was how to know what exact resources you need in runtime, how to dynamically provide them you in runtime versus starting some cluster before and then just hope if this cluster will be enough for your workload. And this is exactly what we addressed with Lithops. Now, so they didn't have to rewrite their application, but they just had to use Lithops API to deploy their functions. Now with Lithops, you don't need to provision any cluster in advance. So the Metaspace workload contains about 12 different stages, and each stage contains different sets of computations. It might be one stage when you need 1,000 parallel tasks with 4 GB of memory. And then based on the results of this stage, there might be second stage needs only 100 tasks with the 4 GB memory. Then maybe it needs more, and so on. So every stage generates some results, and the second stage knows how much resources needed. And this is exactly how Lithops provide them those resources dynamically during the execution. So without having limited to a cluster, Lithops just provision requests those resources in runtime, and then it gets deployed the workloads there, run it, then Lithops collects the results from the stage, and then when Lithops invoke the next stage, it automatically injects the results from the previous stage. So this is completely transparent to the user. And this is completely serverless. There are no any servers behind. So you don't need to keep any cluster, even one machine. It's scaled from 0 to how much you need. And now, so they use it now in production, and they moved from Apache Spark to this architecture, and that allowed them actually to scale as much as they need, and also be very cost effective, because now you only pay for the actual resources your workload needs. So, and this is very efficient. Now, Lithops here use a hybrid approach. So because Lithops supports multiple backends, so in this case, we use Lithops use serverless from IBM Cloud Functions, but it also deploys some of the workloads, some of the stages it deploy to fast VMs that we have, next-gen VMs. So Lithops starts VM, deploy workload, deploy that stage to the VM, then it shut down VM, and then Lithops coordinates all the how to share results from different stages. Now, why they had to use this VM? Because they have some proprietary code that they just wanted to use it into some huge machine with the many CPUs and memory. And this is very good. I mean, it's still they have the serverless experience, even it's one of the stages Lithops deploy a VM for them. Now, I can show you how it works. This is the video, and this is a real video. So I'm going to show you from a VLC. I'm not sure I will run all the video just to emphasize how this works. So this is a Jupyter notebook. And now you as a user, so you choose some configuration, then you choose a molecular database, then you choose your medical image. So here, this is a molecular database, and then you have one up a medical image. And now you begin to run this. Now, we don't need to get into much details what exactly is running here, but you will see now 12 different stages. And for each stage, this dynamically in runtime, Litops will invoke a number of invocation as needed, and you're not limited to cluster anymore. And then based on the results, the next stage, Litops will decide how much invocation you need and then how much memory you need. And this is how it works in production. So you can also have, you obviously can use Litops from your notebooks, or you can use it also from your application if you want to connect it there. So this is an example of the notebook, and the Metaspace, it's another application that they're using. So I can just move it a bit fast, so you will see all kinds of stages here. You see here, Litops decided on 250x concurrent invocations. And this is just an example. In reality, it might be thousands of them. And then Litops collects the results. And this is the user experience that you see here. It's all transparent, and there are no hidden things here. This is how it works. So eventually, if you will run this, they will not run it because it takes about 10 minutes to complete these workloads. But then you will see at the end the results of those invocations. It will be exactly those small medical images. Oh, you see here different stages that are created. And now you can see those medical images that are generated. Let's get to them. Yeah, and this is the results that I said before. So when the process completed, you have the small medical images. And what you do with those small medical images, now you can run all kinds of machine learning algorithms on them, because it's already data that was pre-processed from the huge medical image. You got regions of potential interest, and now you can run all kinds of machine learning stuff on them. So now let's back to the presentation, and to summarize this, so it's very cost effective, and this all happens dynamically in runtime, and you get exactly those resources you need. And then you have simplicity of, you can use now Python notebooks interactive, and you also may change your application to use it. So you saw, I think, both. It's deployed over IBM Cloud, but there is completely no vendor lock-in because Litops supports multiple backends, so you can just take it and deploy it into another environment. And you can process now any data sets because you're not limited to cluster anymore. And also very interesting observation here. So now you can also use this Metaspace application on-prem. Now, why would you use it on-prem? Because maybe you have some very sensitive data that you don't want to use over public clouds, but you want to use it inside your organization. So you can take the same Metaspace application from EMBL. You can deploy it with Litops over Red Hat OpenShift, for example. It's your proprietary. And then Litops supports Red Hat Data Grid, which is InfiniSpan, so you can use it for fast in-memory sharing of temporary results. And so it's all optimized, and you can switch it just by one line of configuration. You can deploy it over public cloud, or you can deploy it over your proprietary OpenShift cluster and benefit from InfiniSpan integration. So that summarizes the EMBL use case. Another example I wanted to show you, it's the data preprocessing. Now, you usually, when you run in particular all kind of image processing, you usually need to do some data preprocessing on them. So either you do a kind of face alignment, or maybe you need to extract colors. And so when you have the colors, you maybe want to run all kind of machine learning, similarity algorithms, deep learning. And there are a lot of examples over the internet, what kind of machine learning stuff you can run on the images. But now, so let's say I have my business logic to align phase, and then I have my images, let's say, in the object storage. So that's a real example. I will need to run about 500 lines of, I call it boilerplate code. I need to list objects from the object storage. Then I need to invoke my business logic. I need to know all kinds of APIs. It will be slow because I don't know exactly where I need to run this code. Maybe I need to run it over some VM. Maybe I want to run it over my laptop, but then it will be very slow. If I want to run it over VM, then I will need, obviously, to spend time to deploy this code to VM to test it. And also this boilerplate code that only knows how to read images. Now, if I use exactly the same business logic with LitOps, it will be 3 lines of code. Because I take LitOps, I point it to my object storage URL, my bucket, and I just tell LitOps, okay, execute my business logic, and that's it. And then it will be deployed and executed in the cloud automatically, and I don't need to worry about VMs or where to run this code, so and so on. So this is an interesting example I wanted to show you, color identification of images. So I show you how I can deploy it over Kubernetes API. So I want to extract colors, find images by similarity, and to extract colors from those images. So this is another very short video I want to show you. Not this one. And so let's say I use my laptop, okay, and I have some image in my laptop, and I want to write some business logic code that knows how to extract colors from this image. And then I do some color identification. I got these codes. So now I can extract colors from those images. I test it on my image in my laptop, how it works. And I see that it works. I can extract colors and see the color space. Then I write another code that I want to match image by color. Like I say, give me please all images that have specific color in it. And then I test it on my single image in my machine that I want to take images that has a color, I think blue or green. Let's see which color I decided to use here, blue. So, and I got this image. Now I'm done with my laptop. Now I have a bunch of images in my object storage. And I want to run this function now at scale in the cloud because I don't have enough power in my laptop. So I just point it to another backend, serverless. I'm using IBM Cloud Code Engine. I'm using my bucket, gvernik US East collected. And there is 15 images there, and this code executes there. And now I found all the images green in 27 seconds. Now I can run it again and extract all blue color images and so on. So you see the simplicity, how I can go from my laptop to the cloud and benefit from all this stuff. I don't have enough time, but we're close to the end. So behind the scenes, a lot of things happens, and I'm going to get into this, but you obviously need to run a lot of code, boilerplate code, if you don't want to use LitOps. And that's also the user experience here. So if you want to run it against Kubernetes, you will OpenShift, you will need to do all kind of deployment definition, job description, user application, how to deploy, how to test. But with LitOps, that's exact user experience you have. You just use function executor, you point it to code engine, and you just run your function, and you get the results. So this slide exactly emphasizes the user experience you have. And to summary what we just saw, so serverless computing, it's a very promising field that but you still need to use the right move there. So to avoid all those complexity, LitOps exactly address those challenges and makes it also very user-friendly, and yet now you can run more workloads against serverless. And what we developed in Cloud Button, it's an open source, so it's exactly designed for this push to the cloud experience, as Pedro described before. We use it internally, IBM. You saw EMBL use cases in external customer. And it also enables all kinds of hybrid use cases over public cloud, OpenShift. And more details, visit Cloud Button, and thank you. And I'm done. So I pass it to Tristan.
Thank you, Gil. 1 second as I share my screen. Okay, and here we go. Hello, my name is Tristan Tarrant, and I work for Red Hat, and I work on InfiniSpan, which is an open source project which implements an in-memory key value store. And during the course of the Cloud Button project, we've worked on enhancing InfiniSpan to fit into this scalable serverless model that LithOps wants you to embrace. So as I said, InfiniSpan is a mature open source in-memory key value store, and we've made some changes to improve its scalability for serverless workloads. We've extended some of its data structures using Crucial, which is another component that was developed as part of the Cloud Button project. I'll describe that in a moment, as well as integrating it with LithOps to enable high-performance data analytics use cases. So we worked on a number of contributions on this together with the team at IMT Paris. And so we had to enhance InfiniSpan's elasticity and scalability. So we achieved that by compiling InfiniSpan, which is written in Java, to native, so as to reduce its memory footprint and increase its startup performance to make it fit better with a cloud model, and introduce a Kubernetes operator so that its management is automatic and transparent. So a system engineer doesn't need to do anything to provision and scale InfiniSpan clusters. IMT worked on implementing mutable data sharing and with high-level abstractions and strong consistency. And this component is called Crucial, and Crucial is an InfiniSpan extension which exposes these constructs to be used in the serverless applications. And we also worked on exploring non-volatile memory support by implementing JNVM, which allows us to have faster access to cold data, so that persistent memory is automatically available after a restart. So this is where InfiniSpan fits roughly in the architecture. Actually, go to the next slide, which goes into a bit more detail. So this is the InfiniSpan storage, in-memory storage running on Kubernetes, of which Red Hat OpenShift is Red Hat's commercial offering. And the InfiniSpan operator manages the provisioning and scaling of the InfiniSpan pods, which have been enhanced with a Crucial library as part of the InfiniSpan stateful sets. And the LithOps clients connect using the intelligent Hot Rod protocol to the InfiniSpan pods. Hot Rod is an intelligent protocol that automatically, transparently supports the scaling of the backend, so that the front end doesn't need to be reconfigured to know that new nodes have been added. So the work that we did on increasing elasticity in order to make InfiniSpan fit better in like a true cloud native experience was to implement new algorithm to reduce the initial transfer of data between nodes. As you add nodes, they need to share some information. And we got some very good results where the startup time was decreased by 66%. And also the being able to process the responses very quickly as soon as a new node has been provisioned. Before this was over 4-second delay, and before being able to process a request, and now it's well below half a second before the first response can be processed. So a very, very sizable improvement, and something that really fits with the serverless model of rapidly scaling. I will describe some of the data structures for mutable data sharing, so that functions can store data, because functions are stateless by definition, but they may want to share data between different stages. They can use InfiniSpan enhanced by Crucial with a number of interesting, highly consistent, strongly consistent sharing data structures. So, for example, a number of linearizable weight-free distributed objects such as longs, lists, and maps, which are atomic. A number of primitives for thread synchronization, such as cyclic barrier, semaphore, and futures, and the ability to define any arbitrary shared object and persist it across the cluster without any knowledge about the size of the cluster or any other consistency guarantees. Everything is handled transparently. The crucial constructs are available in a number of high-level abstractions. So you can use Java, Python, and even shell scripts to access these. So it is very flexible and should fit any model. By using these mutable data sharing structures, we have performed some interesting comparisons with Spark, where the big advantage was demonstrating that we could get faster performance, and in some cases a lot faster performance thanks to the in-memory approach at a similar cost to Spark. So with two of the use cases that we've tested here, logistic loss and logistic regression and k-mean clustering, we observed significant improvements, and as you can see in the table, the cost stayed virtually the same. And we're nearly running up until the end. So the other big part of the research that we did was integrate the new Optane NVM non-volatile memory, persistent, also known as persistent memory storage, that gives RAM-like performance, but also SSD-like persistence. So which gives the ability to essentially be able to scale down without data loss and scale up while maintaining storage very quickly without having to load it from secondary storage, slow HDDs or slightly faster SSDs. And we've seen performance up to 10 times that of a file using a file system. And this can provide significant improvements to a number of workloads. And since we only have a little time left, I think I'll pass the word back to Pedro.
Okay. Okay, so I will share my screen now. Yes. So, okay, let me just conclude. It will be very brief. I know we are brief on time. Just after the nice presentations from Gil and Tristan, thanks a lot. I mean, they really explain very nicely Lithops and Cloud Button results. So some takeaways for you. So we had this overall goal that was to democratize big data thanks to serverless computing. Takeaways for you is that Lithops is a mature serverless data analytic platform already in production. So this is not a research prototype. IBM, after the end of the project, is maintaining it. There is also some startup being created around this. So it will continue in the next years. The code source is stable, and there will be a lot of use cases and tutorials that you can find there. And even in the next months, you will see more exciting results around it. The nice takeaways is that Lithops is multi-cloud. So this memory, this saying about write once, run anywhere, is happening already with Lithops. So you write the code once and you can execute in a variety of computing and storage platforms. The democratizing big data, this pushing the button, is simplicity and productivity. I mean, you just code Python notebooks, and thanks to our data-driven partitioning and provisioning, data scientists don't care about resource provisioning. And this is really useful because you can code your laptop and run it and scale it on the cloud. The other thing is performance and scalability. I mean, you have a huge amount of resources at your hands. It's the serverless supercomputer. You can have aggregate bandwidths of 100 gigabytes per second and launch 1,000 virtual CPUs in less than 100 milliseconds in the cloud. So you can really process a lot of data. And Lithops is really optimized for cloud object storage. If you have a lot of data there, Lithops will chunk it, will partition it, and will give it in parallel to many computing functions. And the last thing that I wanted to say, and that Gil explained nicely, and also Tristan, is elasticity. I mean, really, in cases where you don't know the resources that you need, or where your pipeline are really elastic, and they have different requirements of data computing, with clusters, you will end up over provisioning or under provisioning. And here you will just pay as you go, run dynamically the entire resource that you need, and finish it and scale to zero. So this is my last message. I don't want to take more of your time. We finish here, and now we open this for questions. So thanks a lot for coming to this presentation. Okay, so we now finished. Any questions? Petra? Or I think in the chat, there are no questions for the moment. Okay. Thanks. You can always access the website. There is a lot of documentation and examples. And as I said, it's mature software that you can already use nowadays. And you can contact us. For example, I'm being contacted by different groups, for example, in genomics. Now in the UK, they are asking them to move to the cloud, and they don't have experience in transitioning to the cloud. Take care with the cloud. You can have big expenses if you are not doing it correctly. So we are optimizing how you process data, so we avoid these kind of problems when you transition to the cloud with Lithops. Okay. So, Petra, if there is no questions, I understand that we finished the session. Okay. Thanks a lot for your time.
Thank you very much.
Thank you.